Okay, how's that look? Okay, thanks, Josh. So there's a lot of great surface water talks on the program today, but I'm going to touch on some designing cost-effective groundwater treatment plant topics. And first off, really starts before you get to design. So it's kind of involved for the complete life cycle of a treatment plant, from planning through preliminary design, construction, and operations. All can affect the cost of any drinking water treatment plant. So it's important to think about what those impacts are and what good touch points there are, and opportunities for keeping a project very cost effective. The 10 things that I like to think about when I'm looking at a groundwater treatment plant are: one, starting very early. If you can, try not to skimp on well site areas. I've worked on some well site areas that are very small, and they're absolutely doable. You can put a treatment plant on them, but it really limits the options that you have for how you design the plant and what you do with the residuals. Second, understand the treatment options, how they work. Consider residual handling up front. Number four, demonstrate that your plan is going to work before you design it. The cost savings throughout the project. Hire a designer that's committed to cost savings. Listen to the operators during the design. Work with your contractor. Use standard equipment packages whenever you can, and operate and maintain the plant as well. So we'll go through each of those, and then I'll give you some different examples of different types of groundwater treatment plants. First, don't skimp on the well site area. The picture on the left is a picture from Yuba City, California, where we had to put a 1,200 gallon a minute arsenic removal plant on a site that was 20 foot wide by 40 foot long and surrounded by residential customers on 3 sides. So it was doable. We did it, but there was not a lot of room for chemical feed equipment. There's no room for construction laydown. There's no area for residual handling. So we only had one option: to send it to the sanitary sewer. But the facility could be built. On the right, there's some facilities. The top one is Jefferson PUD at their Sparling site. They were able to build a whole new treatment plant on a site they had already obtained for a well, drill an additional well, and handle backwash water all on an existing site. And then down at the lower site is Clark Public Utilities Carroll Curtis well field, where they have wells and a 10 million gallon a day water treatment plant, but the site was really planned for 50 million gallons a day. So they're going to start expanding that facility in the near future for water from another aquifer to all be served on that same site. When it comes to groundwater, there's lots of different treatment issues, and there's lots of different treatment technologies. So having a knowledge about how all they work and what they can address can be very helpful. Considering residual handling and disposal up front, we talked about some on-site handling options. To me, sanitary sewer can be very easy to handle residuals, but it's not always available, and it's not always the low cost option if you have to pay for what you discharge, and maybe there's often surcharges for high suspended solids in the residual. So coming up with alternative residual handling strategies, whether it's irrigation or an on-site lagoon, can be very cost effective. Into a tank and recycling is very often done now. But in some cases, you have to dewater the solids and dispose of them as well. So understanding how much area you're going to need Are you going to dry it in the lagoon or do some mechanical dewatering, which can be very expensive, or all things to consider. Demonstrating that your plan is going to work is critical to me. I think there's lots of opportunities for saving costs by increasing filter loading rates and maybe even trying to optimize some other process that we'll look at a little bit later. And it's critical to demonstrate that that's going to work before you design the plant. And oftentimes, if you don't do the step of pilot testing or some bench work at least, then you kind of have to be a little more conservative in your design. Being committed to cost savings, I think, means looking at some different ideas for delivering your project. So this is a design build project with a prefabricated concrete building, and it worked great, but not a lot of utilities are willing to go down that route. So I think being open to other ideas about building envelopes, how things lay out, even asking yourself, is it critical to have electrical conduits buried, or is it okay to surface mount them inside your building? Hiring a designer that's committed to cost savings, I think there's lots of opportunities to either save money or add to the cost of a project in the building envelope, in HVAC systems, in instrumentation and controls, chemical feed systems, the room construction or number of rooms, fire handling, and residual handling. And just a quick example, I think all those are fine, and there are good reasons to add them in many places. But it's also important to communicate the total cost of changes that you're thinking about. So you may have a well that has just a constant flow coming out of it with a flow meter and a chemical feed system, and you asked, all right, what if we put a VFD on our well? Well, in some answers to what's the cost of that, you may say, well, that VFD is going to cost $25,000, but there's a harmonics filter, there's additional MCC panels. You may have to have a seismic certificate for the equipment. You may have to keep that in an air-conditioned space. And you probably have to have an analyzer, a new chemical feed system that you can adjust automatically, and the programming to be able to run that at different speeds and different chemical injections. So the cost of adding a VFD isn't just the cost of the VFD, it's all of the associated equipment that goes with it. Listening to operators during the design is really important. They, especially if you're working with a utility that has a similar treatment plan already, they're going to know what they like and what they don't like, and that's really valuable information. If you're working with a utility that doesn't have a similar treatment plant, I love taking people to other treatment plants, talking to the operators that have similar facilities, asking them, what do they spend their time with? What do they wish was done differently? It's just really, really good information. Working with your contractor, you probably all know they have lots of experience and many times better ways of trying to tackle something, or they may see problems with the design about accessing equipment or something that can speed up the schedule. So there's been a lot of projects now that have been incorporating contractor input pretty early in the design, either a construction management at risk, or a CMGC approach, or some progressive design build projects. And I think they're great. They really provide, I think, a higher quality project, and you get that really valuable contractor input up front. The other thing that I like to do that I think really has a huge dividend for cost savings is trying to just use standard packages from equipment suppliers. I like to bid out equipment early in a project, select the equipment that you're going to use, and design the rest of the plant around it. And I don't try to say exactly what the equipment needs to look like. I like to say, here's the water quality we're going to be treating. Here's the performance that we'd like to have. And if there are other things like footprint, height, backwash volume, or flow rate constraints that we want to stick to, that's what I like to put in a specification, and not too much detail on what the underdrain needs to look like or how tall the sidewalls need to be on your filters. That stuff, any of that customization by equipment suppliers costs a lot of money for them to change. So wherever possible, I like to try to work with their standard equipment. And operating and maintaining the plant helps keep the costs down. And really, to me, that means integrating the operators into the whole project early on so that they know what's coming, they know how to operate it, and they own it when it gets turned over to them, and they're happy to have it. They can do a lot of troubleshooting on their own. Not that they don't call and ask questions, but it's really valuable if they're bought into the treatment plant all along the way. So some ideas about using different technology for cost-effective solutions. I mentioned before, there's lots of different treatment technologies, and we see lots of different treatment issues associated with groundwater. So we'll look at some examples of that. One that I have spent a lot of time on over the past 30 years is iron and manganese removal. And there are a ton of ways to remove iron and manganese from water. There are lots of commercial systems available, and it can be kind of complicated to try to figure out what the best way. Sort of the industry standard, certainly if you look at 10 state standards, this is kind of how they set up their typical iron and manganese removal system. That includes an oxidant addition, some contact time with maybe some pH adjustment, followed by a filter system that might include sand and anthracite. It might include green sand and anthracite. The size of the filter is kind of independent of anything other than a filter backwash rate. So they look at 3 to 5 gallons a minute per square foot. And with a plant like this, it's pretty resilient, and it can handle a wide range of iron and manganese concentrations. So with iron, it tends to precipitate pretty quickly. You don't always need a contact tank, or maybe not a very big contact tank. Iron will tend to precipitate, and then you're filtering it out on the top portion of the filter, which is typically some anthracite. Down below is some green sand or some other manganese dioxide media or coated media, and that part of the filter is absorbing the unprecipitated, typically manganese, but sometimes iron as well. The reason why the filter loading rates are so low, 3 to 5 gallons a minute, is because typically the particles are very small when you oxidize them. So 2 to 3 microns tend to be a predominant size for iron and manganese, and keeping a low filter loading rate or a fairly deep bed is important. One of the things that I have worked on over the last 20 years is really trying to increase the filter loading rate. So lots of examples of 8 to 12 gallons a minute per square foot, where we try to eliminate the contact tank and just run with chlorine injected right in front of the filters. And the purpose of the oxidant in this case is really just to oxidize the media. And the media is absorbing both the iron and manganese as it passes through here. Now, this really only works for iron if it's less than maybe 1 to 3 gallons a minute, if you milligrams per liter. If you get up above 3 milligrams per liter, you have to really lower the filter loading rates, because even if you have 10 seconds of chlorine contact time, that will start to precipitate very quickly. So the higher loading rates work great for manganese. They can work at pHs of 6. They can work at pHs of 8.5. And it makes a smaller filter and keeps your footprint down and your costs down. And there are a number of companies that make packages using just this setup as well. There's a long history of very small to some larger and larger plants using this type of setup, and it's typically about half to maybe a third the cost of a traditional industry standard type of design. So it can definitely have some cost savings. This is a large plant that used that type of system. This is the Carroll Curtis water treatment plant with capacity of 10 MGD. Had a $6 million total construction cost, including the wells and the treatment plant. There's additional cost to transmit the water into their service area. But these plants, because they're using packages, all of the piping and valves and filters and underdrains and other associated equipment all comes as a package and skid mounted. It makes it also pretty easy to design and pretty cost effective to design as well. Iron and manganese pilot testing is critical. I think it gives you a chance to test multiple different media, allows you to have competitive bidding. There are some pitfalls that can happen with absorptive iron and manganese removal processes. One is if silica is absorbing to the media over time, it might take a year or 2 years, but it will blind off the absorption sites on the media and it'll just quit working. So it's good to identify that during pilot testing. Also, occasionally you see odd tastes and odors associated with the iron and manganese plant, and it's good to know that in pilot testing so that you can look at ways to mitigate that. And you can also test multiple different treatment flow rates. With nitrate, there are many nitrate removal facilities also being considered around the country. And typically, the lowest cost option is anion exchange. And we see very small and very large anion exchange plants going in. This Glendale, Arizona plant was a 10 MGD water plant, and the equipment package, including the controls and the filters and even the brine recycling and reclamation, was about $1.7 million in 2020 dollars. And that's really cost effective. There's definitely a lot of interest in biological removal. I've worked with one, this microvi technology, that is really interesting. They have bacteria that goes in these encased porous beads, but the system itself isn't that costly. But you have to do quite a bit of post-treatment, and it's exposed to atmosphere, so you're repumping water. And I think there'll be lots of technology advances that reduce the cost of that and maybe even give opportunities to do all of the treatment steps under pressure, so you're not having to break head and repump all the time. But it is definitely an area that works very well and you don't have the brine residual to deal with. Biological ammonia removal is also another area. EPA has looked at some of these systems with very low loading rates, 2 gallons a minute per square foot. I've worked with one system that's made in Japan that did some ammonia removal at about 1 milligram per liter at about 7 gallons a minute per square foot. So it can definitely be done quicker than 2 gallons a minute per square foot. And there are other projects underway for that. People are very interested in PFAS compounds, PFOS and PFOA and other compounds as well. I have completed an assessment for Golden State Water Company where we looked at 3 different sites and different treatment options for their sites. And really, granular activated carbon and ion exchange were the 2 leading options for their sites. And they've elected to actually put them both in at different places. The capital costs aren't terrible for PFAS removal, but there's a lot of operational costs, and GAC takes a lot of empty bed contact time, typically have a lead lag arrangement with contact times of around 10 minutes in each of the lead and lag vessels. And with GAC media in the vessels, the replacement cost isn't too bad. But it's important to know how long and how frequently you're going to have to replace them. With ion exchange, you only need an empty bed contact time of about 2 minutes, but you burn through a lot more empty bed contact times every day. So if you have the same empty bed contact time to regeneration with ion exchange and GAC, you really have to look hard at how frequently you're going to be replacing the ion exchange media much more frequently than you are with GAC. So it's life cycle costs that's a key thing for those removal options. Radionuclides, of course, get more complicated with residual handling, but there are some really cost-effective ways of handling both radium and uranium. With radium, one of the most cost-effective ways to handling that is by adding hydrous manganese oxide, which is a product that you mix up in the plant with permanganate and manganese sulfate, and you take that freshly made HMO, hydrous manganese oxide, and inject it into the water. The radium absorbs onto that HMO and you can filter it right out. And this is a plant in Illinois that was a 3 million gallon a day existing iron and manganese plant that we converted to radium removal, and also added another 4,000 gallons a minute of iron and manganese removal for a really low cost. So that can be very cost effective as well. Just a couple more, hexavalent chromium. There are lots of interesting research projects going on with ways to remove hexavalent chromium. The best available treatments that were listed in California when they had a regulation were reduction, coagulation, filtration, and anion exchange, along with RO. The reduction, coagulation, filtration option was thought to be very expensive, but I worked on some projects for a number of years where we used pipeline contactors for ferrous chloride injection, and we reduced the hexavalent chromium to trivalent chromium, and then add a little air to oxidize the iron and remove the iron and total chrome on a pressure filter. So that really reduced the cost significantly, and it didn't take a lot of chemical. The contact times worked at about 2 minutes, and we only needed about 1.5 milligram per liter of hexavalent or of ferrous chloride to reduce the hexavalent chromium in the wells. In this case, had about 20 to 25 parts per billion of hexavalent chromium. And finally, arsenic removal. Arsenic removal's been around for quite a while. Since the arsenic regulation was lowered in 2001. There are lots of examples where adsorptive media has worked very well. There are still several arsenic adsorbents on the market. The cost of that adsorptive media has not changed that much in the last 15 years or 20 years. It's still, and maybe even gone up, it's still 100 to 300 gallons or dollars per cubic foot, which is pretty expensive. So if you have to replace it very frequently, you're spending a lot of money on adsorptive media. Coagulation filtration for arsenic removal can be done very effectively if you oxidize the arsenic from arsenic 3 to arsenic 5 ahead of time, and you can get some pretty good filter loading rates with some ferric chloride addition, and able to really have a more cost-effective. So that's it. Just the last note that cost-effective facilities really require a sustained focus throughout the project life cycle. And I appreciate you having me. Thanks.
Thanks, Lee. I guess anyone have any questions? I don't see any questions yet in our Q&A box, but we have 3 minutes for questions if there's any out there. Anyone? Type in your questions. You might be getting off easy today, Lee.
All right.
All right, well, thank you again, Lee, for your time. That was a great presentation. Appreciate it. Next up, we have Adam Redding. Adam, you want to turn on your mic, make sure everything's working? Lee, Sophia says great job, so there you go.
Okay, can you hear me?
I can hear you. Yep, perfect.
Okay, perfect.
You want to go ahead and share your screen and get started?
Yes, sir. Thank you. Now, 1 second. Pulling up here, I hope. There we go. Thanks, Josh.
No problem.
Thank you, Mr. Adele. I wanted to echo one thing that Lee said, and that is that as an equipment supplier, I would really advocate also for sticking with the standard equipment that is supplied by the vendor. In particular, it's really important when you have a system that's NSF certified and those components are certified, and if you go into a project changing the components, you lose that certification and you lose the cost savings that could come with that certification or should come with that certification. So today I'm going to talk about some work that we at Calgon Carbon did with Lehigh University through a grant that Pennsylvania offers to look at ozone BAC and look at the activated carbon properties and how they relate to removing a couple emerging contaminants. And those contaminants that we looked at in this set are some of those that were studied or are being studied under the UCMR-4, the Unregulated Contaminant Monitoring Rule, and just those in particular under the EPA 530 method. So this talk's going to be a little bit different, a little bit more, I should say I'm going to get into the weeds a little bit rather than a broad overview. But at the end, if there are questions, I could talk about just about any activated carbon topic that should come to mind. But let's dig into this. So we had a tertiary treated wastewater that we installed an ozone BAC pilot unit downstream of that water to then look at several activated carbons not just from the perspective of grain size and other properties like effective size or uniformity coefficient, those things that would influence particulate removal, but to look at how the surface chemistry of that carbon might impact things like the contaminant removal. And then also one of the outcomes was just how serviceable that carbon is. In other words, the backwashing frequency of that carbon was something we discovered that we're investigating further. That was a bit of a surprise. So a results preview, this is to hit you over the head with a 2x4, as my advisor liked to say in school, to keep people's attention. Don't drag out a long story, but at least give them something to look at from the beginning. And that is butylated hydroxyanisole, or BHA. This is a food-grade antioxidant that unfortunately has some possible carcinogenic effects, but it's still present in some of our food supply. But looking at this through the influence across the ozone system and then across the last carbon in the data set was one that had additional nitrogen added to the structure in the production process. So the positive takeaway here is that we don't see a lot of removal, at least steady removal through the ozonation system, because this is an antioxidant, so it would be resistant to degradation. But we do see, most likely through biological methods, just not straight absorption, removal through the activated carbon system to a fairly decent degree and to some extent below the reporting limit there of about 30 parts per trillion. So to keep that in mind, a part per trillion, to rationalize that, because that's an extremely small amount of material, one way to think about it is the size of a cowboy's hat versus the size of the state of Texas. You can find 1 part per trillion, you can find that cowboy. So that is something I'll admit I stole from an Alcoa presentation they put together years ago when we were all interested in PCB removal. So again, through this carbon, and we'll see this across most of the carbons, a very good, or a decent, or I should say an effective removal of the butylated hydroxyanisole antioxidant. So I'll talk about the emerging contaminants now, just to give you some background, understand where we might be getting those from and why they're present in this wastewater. The presence or where they're coming from is a bit of conjecture, I'll admit, but at least I'll give some background on where or how these could make it into that stream. So here's this compound. First thing there to take away is the log KOW, the oxinol water partitioning coefficient, is positive, 3.5. That says that through pure absorption, this should be removable. This compound's added to numerous parts of our food supply where we're trying to resist oxidation or prevent oxidation. Most notably those products that have a high oil or fat content. Interesting to me there to see that they may be added to beer. I do consume a fair amount of beer, but I'm not sure that's in any of them that I do consume. I'd like to know, however. So the NIH says, and I assume this would also echo what the EPA says, reasonably anticipated to be carcinogenic. Minimum reporting level by this method is that 30 parts per trillion, so 30 cowboys in Texas. And this is how the EPA assessed the results. They didn't set a limit within the UC Mark 4 for where they thought it might impact human health, but they did just study it at the reporting level. So within UC Mark 4, not a lot of detections in public water supplies, and this talk's more geared at reuse, but within UC Mark 4 we had 8 utilities that saw it in their finished water above that 30 parts per trillion. So next compound in the set, this is quinoline. I'll admit we didn't see this repeatedly in the influent water, so we have a sparse amount of data, but nonetheless some data that suggest what we might see at full-scale treatment. Log KOW is a little bit lower. This means it's a little bit less removable with activated carbon through straight absorption, but it should still absorb at that level. You can see this from numerous facilities that might be doing petroleum refining, wood preservation. Again, I can't speak to exactly why it's in this wastewater, which is for the bulk. It's a municipal wastewater. This is not industrial wastewater. EPA class, probable human carcinogen, the reference concentration. So this is different than the detection limit for the last compound. This is where EPA would be targeting a limit to say, okay, if it's below this level, would be safe for consumption. Above this level, we'd expect increased cancer risk. So in this case, quite a few more detects than the BHA, the butylated hydroxyanisole, 63 public utilities with reference concentration greater than that 10 nanograms per liter. Finally, orthotoluidine, again, another compound under this EPA 530 method. While KW is lower, should still be absorbable based on my experience. Manufacturing intermediate, just like the quinoline, also used in making dyes and pesticides. Interestingly, if you read about this, a beautician or someone doing any type of hair dye might be exposed to this compound at higher levels than others in the population. It has been positively identified as carcinogenic. Here, the reporting level is the 7 parts per trillion, so 7 cowboys, and then 76 detections in the UCMR4 greater than that minimum reporting level. So all the work that we did here was then evaluated at this reporting level for these compounds, or at these, excuse me, I should say, reporting level for these 3 compounds versus the reference concentration in the wastewater samples. Finally, this is another set of contaminants we looked at. We really expected to see them. There's a tremendous amount of data out there that supports that if you take a wastewater, or any water for that matter, with a high amount of nitrogen content, that you will end up with nitrosamines in the effluent of the ozonation system. So we, unfortunately, and this is what, again, we were really looking for, wanted to get a lot of data on this, just to add to the larger data set, but we could not detect them. We repeated this through multiple sampling rounds, non-detect between 0.5 part per billion and 2 parts per billion. Perhaps at lower levels we would have seen them, but again, we did not find this set of compounds. So a little bit disappointing there, but nonetheless, we had data for the UCMR compounds that I mentioned. So the activated carbon properties, I won't spend a lot of time here. I'd argue that even as a carbon person myself, this will put a lot of people to sleep. Looking at 2 different mesh sizes that might be applied in a surface water treatment system, more typically in a pressure vessel rather than a gravity contactor. So we took the first 2 carbons and then applied 2 different treatments. So we had one that was oxidized or oxygen enriched, and another that was treated with a nitrogen-bearing compound to impart more nitrogen in the structure. So what this does is this then changes the charge on the surface. What we'd expect from the oxygen-enriched carbon surface is a more negative surface. So phenolic compounds, carboxylic compounds on the surface of that material when it's sweated. For the nitrogen-enriched material, our data shows that we're looking at pyridinium functionality, so this would be a positive charge on the surface. So we're going to have some influence here between the bacteria that colonize the surface and that surface charge, and that's what we'll see in some of these results. The carbons do not vary terribly widely in the apparent density. The nitrogen-rich one was heavier, relatively speaking, but iodine number between about a 900 and 1,000, so not a large difference there in just total expected surface area. You see that contact pH there, that tells you about the difference that I mentioned earlier. Positive surface, acidic functionality, carboxylate, phenolic, that's going to be the negative charge. And then a high contact pH, and finally the molasses number, which should tell us something about the degree of the mesoporosity or the middle-sized pores versus the microporosity. Takeaway there would be that we would expect some bacteria to colonize the mesoporosity, but bacteria are too large to make it into the microporosity where the compounds absorb. Next, to look at the pilot configuration. This is fairly straightforward. We have an ozonation system with an ozone contact chamber, or 2 contact chambers. We have a desiccant to supply dry air to an ozone generator. And then this water then goes to a reservoir and is repumped into the activated carbon columns. Target here from an ozone dosage perspective was to hit roughly 1/3 of the TOC, or the total organic carbon of the wastewater. In some cases, you're going to see a higher dosage than that. This might be on the low end, but nonetheless, that was what was used in this study. We did pre-filter the water coming into the system just to remove some of the residual particulate and reduce the needed frequency for backwash. And then finally, we have an online ozone monitor and temperature monitors. And the pilot configuration, 36 inches of carbon, a 3-inch column diameter, shooting for a contact time of 10 minutes. We could have scaled this system to match a higher hydraulic loading rate, which is what we'd expect at the full scale. But with 10 minutes of contact time, we wanted to exacerbate the influence of the microbial community. So in other words, give them as much time as possible to degrade these compounds so that we could see as much difference between the carbon if there was indeed a true difference. And the backwash trigger for when I'm going to talk about the backwashing results, that was 10 psi of differential across the carbon column. So the graduate student operating the system, every time it hit 10 psi, he'd come in and backwash those. Typical backwash frequency was 15 to 20 minutes at a 30% bed expansion. Let's dig into some of the results. Looking at the butylated hydroxyanisole removal, we saw that all of the activated carbons applied here were able to remove this compound through what we expected was biological removal. The one key takeaway here, the reason we think this is biological removal and not absorption at this part in the experiment is because prior to the April 14th date that you see there, this system had been operated since February. The data starts April 14th because that is the point in the study where we gave up on the NDMA sampling, not seeing any detections, and moved to look at other compounds. And this here is where we began looking for the UCMR4 compounds. So this data, you may take away that the nitrogenated material had a little bit better and more consistent removal of the BHA. I would argue that that's not enough data at that point, or not a large enough difference to say that there is a consistent removal. Interestingly here, we can look at the dates and say, okay, April 14th through June, roughly 2 months later, that's the change in the seasons in Pennsylvania, and the same also in the Northwest. So we would expect a change in the influent water temperature. And let's plot these results against that value. So influent water temperature started around 15 degrees C in April and jumped about 23 degrees C at a steady state. I would say that if this is biological activity, we probably saw the influence of a higher degradation rate. We know that at a higher temperature, we should expect more biological activity. So this to me suggests that we see a higher removal at a higher temperature. We're actually continuing to run this system through a phase 2, and we'll have additional data to see when this drops back into the winter to see if our degradation rates decrease. My hypothesis is in this case that we are going to see a drop. So quinoline, I mentioned earlier that we did not have a lot of data to support removal or consistent removal, and that is because the influent concentration was very close to our detection limit. So we would go from 0 to 40, and it varied quite a bit. Looking at the data, the best I can say at this point is you could see 25 to 100% removal across the combined system, but until we had a lower detection limit or higher influent, pretty difficult to make a conclusive takeaway there. The samples taken at higher water temperatures are those, though, that were regularly below 100% removal to below the detection limit. And looking at orthotoluidine, again, 7 parts per trillion, 7 cowboy hats in the state of Texas. All the samples post-GAC showed 100% removal. So detection limit there is 7, influence 11 to 20, so you're looking at double that concentration, but still not terribly conclusive, but I'd argue that they're positive to say that there is consistent removal occurring. So TOC reduction, this was somewhat confounding. Perhaps it makes sense in the context of the wastewater treatment system, that we would have seen more degradation in that system, or excuse me, that the compounds coming into our system were more recalcitrant. We did not see a large decrease over time, an average of a 12% decrease, and maybe some temperature impact where you see lower levels coming in, but not something I would say that was a large TOC reduction. One thing to keep in mind, though, is when you look at these concentrations, this is 10 parts per trillion versus compounds that we were looking at, excuse me, this is 10 parts per million versus compounds that we were looking at that could have been 10 parts per trillion. So the compounds we're examining in the UCMR4 are a millionth of the TOC concentration. So any change in TOC would not show us what we were looking for in terms of the target contaminants. So this could vary quite a bit, and we would still not expect to have it influenced by our target contaminants. Finally, dissolved oxygen, we saw a pretty steady state removal of DO through the pilot columns. This would suggest that they are operating aerobically, and also would support that we would have a relatively fast process through that system, given that aerobic degradation is almost always faster than any anaerobic process. Average decrease about 61%. Here, no marked difference differences between the carbons are visible. So up until this point, the UCMR4 compounds, they're removable. That's great because we're looking at compounds that are recalcitrant. That's why they're making their way through the wastewater treatment system. They're making their way most likely through our bodies and into the wastewater as we are the vehicle for the contamination there. But this was a very interesting result here. And as a water treatment plant operator, operating a surface water facility where you're backwashing at a regular rate, this is an extremely valuable and I'd argue the most valuable conclusion out of the work. So we have the nitrogenated material, and you'll see that in the gray line at the top, net positive surface charge. We have the two untreated materials, which regardless of the difference in the particle size, where a 12 by 40 is about a 1 millimeter particle, 8 by 30 is about 1.5 millimeters. Those quite similar in terms of the backwash frequency. Again, 10 psi trigger. And we look at the one carbon that was oxygenated, and it's quite a difference in the backwashing frequency. We have this entire study, and they're both, or excuse me, all carbons, all four, treating up to 10 to, I'd say now we're about 15,000 gallons of material, of water. And we have about a 20% less, or 20% decrease in backwashing frequency. So this is quite valuable. This suggests that you would, with this material, if it were applied at the full scale, be able to operate much longer between backwashing frequencies, which means that your ability to produce water is higher and overall just cheaper to operate, less wastewater and less time spent just running those systems or backwashing those systems, maintaining them. So this is going to be evaluated in a second round of the work. And from a particle retention standpoint, we now need to go back and look at the turbidity. This is not something that we examined in great depth in the first part of the study, because we need to confirm that all these materials are providing the same particulate removal, because that is, from a physical standpoint, the goal of one of these systems. And if this is indeed what we're seeing, this net negative surface charge is allowing a longer runtime, what that suggests is that our flock, any particulate, is able to penetrate more of the bed, and that the entire bed itself is operating or participating more in the particle removal, so that we're retaining particles throughout the whole bed depth. So this is pretty valuable. It also says that we're removing them effectively during the backwash, since we can go longer between these cycles. So this would have to be something that we'd present in round 2 of these results. And hopefully we'll see this again and be able to bring something like this to market, where it's quite beneficial to the operator, to the utility. So to recap the conclusions, BHA, quinoline, orthotoluidine, they're removable. Even with a little bit of data for quinoline, orthotoluidine, I think it's a positive result. Higher temperatures is what we would expect. Allow a higher degree of degradation. We'll be able to see if that ties in as we get into the cooler months in Pennsylvania, now making it here through the end of summer and into fall. DO reduction was steady, but not a large drop in TOC. One thing we can examine here in the second part of the study is if a higher ozone dose will hit more of that, but did not appear to be that those responded very large to the ozone. Another benefit in an ozone BAC system is that you should see that the ozone oxidizes the TOC molecules, or the molecules that comprise the TOC, so that they are more amenable to biological degradation. We did not in this case see that, but again, it did not impact the removal of the target contaminants. One thing to tie into Lee's prior presentation is that we are going to look at PFAS compound removal through these systems. And not removable biologically. That has been very well established, that these compounds are, one, not removable by oxidation through just about any oxidative process that we currently apply, and are not removable, at least in current systems, through biological removal. But we would like to see how the physical absorption of those is impacted by operating this system with a biofilm on the surface, which is going to be very valuable, since they're targeted for removal and water reuse, since we certainly don't want to add them back into our reclaimed water, or allow them to make it their way to their reclaimed water. So modifying the carbon surface did not seem to impact the biofilm, did not impact the degradation, but did appear to improve the backwashing performance. So this is pretty cool. On the ongoing work, like I said, we're going to repeat the test. It's already continuing. The grad student's back on site doing his part, and see if we can hit this reduced backwashing requirement again. We're going to look at some other grain sizes, because frequently you apply like an 8 by 16 or 8 by 20 material. Finally, continue to look at these EPA Method 530 compounds, and we'll occasionally scan for some others to see if they pop up in the wastewater. And as I mentioned, PFAS compounds, that's something we're certainly going to look at. So I'd like to thank the City of Bethlehem, PA, the wastewater treatment facility, letting us on site, especially during COVID, where we just kept ourselves separated from the operators and just allowing the work to continue, since I know we all closed down for a while. And finally, for the Pennsylvania Infrastructure and Technology Alliance for funding the work, or part of the work. Thank you, Josh. That concludes my presentation.
Thanks, Adam. Appreciate it. If anyone has any questions, please do type them into the Q&A. I was wondering, Adam, if you had an idea of why you don't think you were getting good TOC reduction across the ozone treatment system, if you had any theories about why that might be the case.
The most likely thing is that the compounds comprising the TOC were there at that part of the treatment simply because they already could not be degraded in the existing system. The Bethlehem plant is planned for some upgrades, which I do believe are needed for their water quality there. Not that they're not doing a good job, but there could certainly be some improvements. But whatever is going on there at this point, those have already apparently been oxidized enough or attacked enough that they're not going to degrade further. It was very surprising.
Great, thanks for your input. It looks like there are no other questions. You're getting off easy today too.
Oh, wow. Thank you very much, everyone. Appreciate your time.
Yeah, I really appreciate it, Adam. We're going to take a 10-minute break, and we're a little early, but we'll reconvene here at 9:40 and get started at 9:40. It looks like our next presenters are already online, Alex and Mike. So at 9:40, we'll reconvene. Go ahead and take an 8-minute break until then. Thanks, everyone.
Thank you.
Hey, Mike, you want to test your audio, make sure that's all working?
Absolutely. How's that sound, Josh?
Sounds good.
Awesome. Great to be here.
Join us
Two
today.
great presentations.
Yeah, Alex, how about you? You want to test your audio, make sure it's all working good?
Yeah, test. Can you hear me all right?
Looks great. Thanks.
I have a fan on, but I'll turn that off.
I can't even hear it, so I think it's okay.
Oh, really? Oh, good.
We'll give folks another like 30 seconds, and then we'll launch a quick poll, and then we'll get started with your presentation, Mike.
Awesome. Sounds good.
All right, all sitting in the background here.
Yeah, sounds good. Yes.
Might be the first conference that's ahead of schedule I've ever been to, so this is great.
I know, that's what I was just thinking. Here, I was gonna edit our times, but it's a screenshot, so I can't. Darn.
Some fancy text box overlay.
I know.
Well, maybe I'll make up for it and make us go way over. How about that?
Oh, there you go.
Be a positive there.
And I apologize to Lee and Adam. I just realized I forgot to do their introductions, their bios. So I apologize to you guys. Bear with me for just a minute. Okay. All right. I will launch a quick poll. Now that we're back at 9:40 here, a little ahead of schedule. So just want to get a sense of what everyone's level of understanding of ozone biofiltration is as a treatment process. So basically, are you just learning about it now? Do you have some understanding of ozone biofiltration, or do you have high understanding? If it's something that you guys currently use or have designed in the past, that would be a high level of understanding. Looks like we have a good smattering of folks that have some understanding, others that are just learning about it now, and a few that have a high understanding as well. So looks like we have a good variety. We'll give folks another maybe 15, 20 seconds to respond to the poll, and then we'll get started with Mike's presentation. Okay, here's the results. And while you're looking at the results, I will introduce you, Mike. Dr. McKee is a postdoctoral fellow with Drinking Water Research Group at the University of Toronto, Canada. He's examined the optimization and characterization of biological filtration since 2013, completing his Master in Science in 2015 and his PhD in 2019. He has been investigating biofiltration in the Pacific Northwest in collaboration with the Eugene Water and Electric Board since 2018 and looks forward to continuing research in this region in the future.
Awesome.
Go ahead and share your screen, Mike, and go ahead and get started.
Excellent. Thank you very much for the introduction. It's great to be here today. Really excited to be able to participate. Excuse me, as part of this short school. I was really excited to actually be able to come to Spokane and come to the conference, but obviously that got kiboshed. So we're talking today about some of the full-scale monitoring approaches that we've looked into regarding biofiltration conversion and the impact of intermittent operation. And this, as Josh mentioned, was done in collaboration with the Eugene Water and Electric Board, specifically Toby, Jared, Lonnie, and Ray. And this was done as part of the Water Research Foundation Tailored Collaborative. So it's been a great program, and it's been really exciting to be able to participate in biofiltration research in an area significantly different from Ontario. And building on the previous presentation, we're going to be talking about biological treatment, but in this particular instance, we're not going to be looking at the impact of ozone. It's just going to be straight biofiltration. So the Hayden Bridge filtration plant is operated by the Eugene Water and Electric Board. It treats Mackenzie River water. They add alum for coagulation and seasonally or event-based carbon and polymer for taste and odor control and coagulant aid. Also, in the past, they used chlorine for a pre-disinfectant, and that was primarily to provide some pH suppression and improve treatment performance. So that goes through settling, and then they have anthracite, coal over sand filtration. And that's followed. I just wanted to make sure none of those notes were for me. So disinfection at the plant's provided with chlorine into a reservoir, and then sodium hydroxide is added for corrosion control before distribution. So a lot of the driver for this project that we participated in and are finishing up now was actually the elimination of chlorine gas and conversion to on-site sodium hypochlorite. So they've recently commissioned their on-site sodium hypo facility, and one of the design considerations for that was the elimination of pre-chlorination. So if they could eliminate pre-chlorine, that would reduce their chlorine requirements and in turn have a more effective and more cost-efficient on-site production facility. Their plant is currently rated at about 88 million MGD, but daily production is currently less than 40 typically. And what that allows them to do is actually rotate through their 14 dual media filters. So they're not running all 14 filters continuously. They don't have any need to operate that many filters. Instead, they'll operate a small subset of those and shut them down following backwash. This shutdown period during warm water during the summer months may be as long as 3 to 5 days, but in cold water conditions, it could be 7 to 10 days. Typically not longer than 7, but there are some situations with low water demand that they may have a filter sit for up to 10 days at a time. And then before they bring these filters back online, they provide filter to waste to reach a turbidity target, I believe about 0.04 NTU. So when we talk about biofiltration, it's always really important to consider your definition of biofiltration. In the past, there's been a lot of biomass or performance-based thresholds that have been proposed, but that doesn't necessarily apply in every facility. In Ontario, we have a lot of surface waters that are relatively high organics, 5, 6, 7 milligrams per liter. And that can support a lot of active biomass just because there's a lot of substrate for them to consume. The Mackenzie River is relatively low organics. We've been monitoring DOC for the last 2 years and see typically somewhere between 0.5 to 1.2 milligrams per liter. So a small fraction of what we would see in some of the other surface waters. And that really doesn't necessarily promote the growth of bacteria to the same extent that higher substrate loadings would. And the goal of this was to use the existing anthracite media. This is a picture of a GAC media for comparison, but you can see a pore structure, but before biofiltration, it's relatively clean. If we allow operation without a disinfectant residual, in this case, if we eliminate pre-chlorination, we can actually then start to see the growth of some microorganisms on the surface. And that colonization is really what we're hoping will degrade or consume the substrates in their settled water. So with these considerations in mind, we had a few project objectives. And the first was to evaluate the impact of pre-chlorination elimination. So at this facility, they had no experience operating a biological treatment plant, and they wanted to know how long it would take for the filters to go biological. What are some of those operational impacts? How's that going to impair water quality, or how's that going to change their treated water quality and production ability? Are they going to have to change full-scale operation? We also wanted to identify some effective monitoring parameters. And a lot of times monitoring of biofiltration processes just focuses on water quality. Do we get the same dissolved organic carbon that we used to have in the filter effluent? Do we get THM or HAA biodegradation? Do we get improvements? Do things change in the water quality? But we also wanted to look at biomass and see how we could characterize that both in quantity and activity. And finally, perhaps the most important thing is, how does this conversion impact production? One of the biggest questions people often ask is, will I have to backwash more? Will the biofilm clog up the pores between media and result in increased maintenance? And we wanted to ensure that their plant could continue operating the same way as it has in the past, despite the conversion to biofiltration. And finally, we wanted to examine biofilter shutdown up to 96 hours between filter runs. So 5 years or so ago, we started doing some work on daily shutdowns for 8 to 12 hours, and it was kind of an unheard of thing. And as we continue to talk about this, more and more plants are saying, yeah, we run biofilters and shut them down, and seeing if there's going to be an impact to preventing substrate loading for up to 4 days at a time is going to be really interesting and one of the key elements of this project. So a brief overview of the Hayden Bridge filtration plant pilot. It takes raw water from the Mackenzie River and applies inline coagulation, which is then sent to a chlorinated pilot filter. This chlorinated pilot filter has chlorinated backwash, but is unchlorinated into the filter. Raw water is also then coagulated and added with polymer. That's sent to full-scale settled water. We then draw from the full-scale settling basin and run that water to a control pilot filter, which is operated continuously, and an experimental pilot filter, which was operated cyclically or with shutdowns between filter runs. And finally, those results were compared to a full-scale filter. We used the same filter throughout the study, and we wanted to compare full-scale operation to pilot-scale operation. So these are the chlorinated and control pilot filters on the left. They've been installed and in use for full-scale plant optimization for a period of a number of years, even before this study started at the facility. As part of the startup to this project, we also had them build a third pilot filter, and I will give them full credit. They make some of the most well-designed, well-thought-out pilot filters, and I think it's because their operators who built them also have to operate them and utilize them day to day. So they've really thought about all the small details, and if you have any questions about pilot design, pilot building, I would certainly implore you to get in contact with the people at eWeb, because they really are some of the best I've seen in terms of developing, installing, and operating pilots at their facility. So just to highlight some of the details, the full-scale filter was operated as necessary for production. We didn't limit their operation or force them to stay on a schedule. And that has a chlorinated surface sweep. So the backwash itself is unchlorinated, but the surface sweep is a chlorinated feed. The chlorinated pilot filter was operated continuously and utilized for full-scale plant optimization. So the coag dose in that particular filter may not be the same as full-scale, and that had a full chlorinated backwash from the chlorine reservoir. The control pilot filter was operated continuously, and it had a dechlorinated backwash. All backwash water was dechlorinated with ascorbic acid or vitamin C and measured to be 0 milligrams per liter before backwash. The experimental pilot filter also received dechlorinated backwash to mimic the control filter, and the shutdown duration increased on a 2-week schedule. So it would be 2 hours for 2 weeks, and then 4 hours for 2 weeks, etc., throughout the different trial conditions. Phase 1 of this project, we wanted to look at filter acclimation and how biomass developed following the elimination of pre-chlorination. So the experimental filter was commissioned in December 2018. Anthracite and sand was harvested from the full-scale filter, and this filter was operated continuously to mimic and hopefully reproduce the results we see in the control filter. The control and chlorinated filters, as I had mentioned, had been in operation for a number of years prior to this study and were assumed to be acclimated to the biological conditions which we could expect. To evaluate biomass development, we used ATP, or adenosine triphosphate, and this is an energy carrier that is present in all cells and is indicative of the amount or concentration of biomass on the filter media. One of the interesting wrinkles that we threw in here is we also looked at biofilm activity through enzyme activity. So these assays actually are able to evaluate biofilter function, or what they're able to biodegrade, instead of just the number of bacteria present. And acclimation in this particular case actually took place under kind of the worst case scenario with cold water conditions. Trying to acclimate a filter in December when water temperatures may be in the low to mid 40s is certainly a lot more difficult than in the summer when you have high biological activity and potentially more substrate availability. So when we looked at biomass development over the period of December to the middle of March, we saw that the control biofilter had relatively stable biomass density, and it didn't really change very much, which was nice to see that it was well acclimated and performing biologically. The full-scale filter, which again had chlorinated surface sweeps, had generally good biomass development, but it was lower than the control because of that exposure to chlorine that it would have. The chlorinated pilot, which received chlorinated backwash, had similar results to the full-scale filter, and that kind of confirmed that chlorine in the backwash or exposure to chlorine may impact that biomass development. And then when we look at the experimental filter, we saw generally low results through December, January, and it was really only starting in February and March that we saw some sort of increase. And what we can see from this is that biomass development, as defined by ATP, takes roughly 3 to 4 months. And previously, the literature has indicated that a threshold of about 100 nanograms per gram media would define biological acclimation. And that's kind of what we defined here. Over a period of about a year and a half, the experimental filter didn't ever reach the same ATP concentration as the control biofilter. So we also looked in parallel at biological activity to see what biofilter function looked like. And we can see that each of these filters showed a similar trend. The control biofilter had the most activity, full scale and chlorinated had subsequently less activity. And esterase activity is really just looking at the degradation of a simple organic carbon compound, just a single carbon acetate. And what was interesting here is that we saw similar activity to the control biofilter within about 2 to 4 weeks. So despite the fact that the biomass concentration was much less, the biological function, or the ability to biodegrade this enzyme substrate, was equivalent and greater than those filters that it was equivalent to the control and greater than those filters which received chlorine in a fraction of the time that biomass would tell you it took to acclimate. So to summarize that briefly, similar density or biological acclimation by ATP was observed in about 3 to 4 months, and it's predicted that cold water may have slowed the growth and development of these bacteria. However, biological activity was similar to the control in less than a month, and this may be a better monitoring parameter because it really tells you what the potential performance of the filter is, instead of just telling you how many bacteria are present. And we did see similar filtered water quality from January to March. So when we looked at DOC, THM, HAA formation potential, we did see similar results between those filters and relatively low organics removal. So less than 5% by DOC. Following the acclimation, starting in April of 2019, we started to do some warm water shutdown testing. And we wanted to evaluate shutdown durations of 2 to 48 hours. Each condition was evaluated for 2 weeks at a time. Samples were collected weekly to ensure that we could see some seasonal variability and compare the results directly between the control, experimental, and chlorinated filters. We did biomass characterization with ATP and enzyme activity again. We did organics characterization, DOC, UV254, and some DBP precursor formation potential. And what we did was we chlorinated our water samples for 24 hours and then monitored or evaluated the concentration of THMs and HAAs that formed, as well as some online water quality, DO, pH, turbidity was conducted at the facility. And finally, we also looked at unit filter run volume. We wanted to see how production compared between those different filters to see if we were getting impaired production or if we could get the same level of production with shutdown. And we look at ATP, the control had a slight dip through the 16 and 24-hour period, but that was similar with the chlorinated filters. So the full-scale filter was pretty stable throughout that period, and the chlorinated pilot showed a similar trend to the control filter. And when we look at the experimental filter, we see a similar trend to the control. So there was really no impact with shutdown to the control, looking at it at shutdown times from 2 to 48 hours. And one of the other things that was actually kind of interesting is there's kind of this delineation around 12 to 16 hours. So prior to about that period, we see that the ATP on the biofilter media was a little bit higher at a sampling time of 1 hour compared to 4 hours. Whereas after that point, we saw less ATP following startup. And what this is kind of telling us is that there's the potential for the filters to take a number of hours of operation to reach steady state conditions. We also looked at enzyme activity, and we see a very similar trend. So for shutdown durations of 2 to 12 hours, the activity on the experimental biofilter was relatively lower than the control biofilter. So if we just look at the blue and the yellow, blue squares and the yellow diamonds, we see that the experimental biofilter had relatively lower enzyme activity or biodegradation potential. However, for shutdown durations longer than 16 hours, we actually see that it's relatively higher in general. So what this is telling us is biofiltration shutdown may actually provide some selective benefit by promoting the growth of bacteria or production of enzymes that relate to carbon degradation with shutdown. And it seems that at this facility, there may be a delineation between 12 and 16 hours that really provides some sort of benefit to those biofilm communities. So, quick summary, similar ATP was found on the control and experimental filters. And what this kind of tells us is that the biomass community or the biofilm community isn't really impacted by shutdown. It may be related to substrate, but we didn't see any definitive trends or water quality indicators for this. There's relatively more biomass or relatively more activity in the biomass with extended shutdowns, which may tell us that it's a preferential operational procedure. But we really didn't see a relationship to temperature. Most people would tell you biological processes are dependent on temperature, and we didn't necessarily see that trend. When we look at organics removal, and we really just want to look here at the orange, gray, yellow, and green bars to look at the filter effluent. If we look through the various shutdown durations, we don't really see a huge difference with respect to the removal of DOC from raw water. There's a few instances where you might see a peak or a dip, but for the most part, the orange and yellow bars are generally similar. And this tells us really that similar DOC removal was achieved by all of the filters. So this is good that coag, floc, sedimentation, filtration, with or without exposure to chlorine or shutdown, provides similar organics removal from the plant. And again, it's important to note that most of these DOC concentrations were less than 1 milligram per liter. So an 80% reduction really translates to about a 0.2 or a 0.3 milligram per liter effluent concentration. Similarly, when we look at THM and HAA, or THM formation potential reduction, if we compare the dark blue bar to the orange bar, we see generally similar results. And again, this test tells us that biofilter shutdown doesn't necessarily impact treatment performance for the reduction of DBPs. So in summary, similar effluent water quality was observed, and there was no statistical difference between any of the filters. We also looked, as I mentioned, at other common monitoring parameters like pH, DO, UV254, and found that they were generally poor indicators of performance for comparison between these filters. The resolution is relatively limited. It's hard to put faith in the second or third decimal of a pH or DO probe. And there's no trends related to the regulated parameters. So if we're trying to get insight into something like THMs or HAAs, these parameters weren't able to give us those indicators that we were hoping for. Ultimately, what we took from this is that biofilter shutdown did not impact performance with respect to water quality. And that was really good because we wanted to ensure that they could continue to operate their plant the same way without having significant water quality issues. When we looked at filter production, we just looked at the 3 pilot filters. They were designed the same way, same type of plumbing. And we see generally a nice trend in correlation between the chlorinated and the control filter. The control filter has a little bit of a higher UFRV than the chlorinated filter, but we don't really see a lot of difference between the two of those. However, when we look at the experimental filter, which was shut down for 2 to 48 hours, we see a significant improvement with shutdown durations greater than 12 hours. So I talked about esterase activity and biological activity increasing with extended shutdowns. And we see the same thing here where these filters are actually much more efficient at producing water with greater than 12 hours of shutdown following a backwash. And this was really interesting to me. The operators weren't at all surprised. They see this at full scale all the time, that they get much better filter performance when they let a filter sit. But it was really interesting to see that there's something perhaps in the filter operation that is impacted by letting the filter shut down between filter runs. So to summarize, warm water testing, shutdown of greater than 12 hours increased production by up to 100%. Water quality was not impacted. Extended shutdown may improve biological performance when it's compared to the continuous operation. So there's likely some benefit to that for both biological, physical, and chemical treatment objectives. And what this really told us was full-scale biological operation was viable. Eliminating pre-chlorination, going to a biological filter wouldn't necessarily impact performance of their plant. We also did cold water testing. We just completed this in March of this year, right around the time that the pandemic struck. So that was interesting to get finished up just in time. But we extended the shutdown durations up to 96 hours to better reflect expected conditions at full scale. So when we looked at biomass density, on average over that period, there was a decrease from full scale to chlorinated, and that chlorinated backwash perhaps had a bigger impact during cold water conditions and reduced the amount of active biomass. Compared to the control, and the experimental filters. And what we see, and this is something to take note of in cold water conditions, is that the experimental filter monitored 1 hour after filter startup was often impacted when compared to 4 hours after startup, which we considered to be steady state. So after startup, there may have been some stress on that biofilm, which reduced the amount of active ATP. However, after 4 hours, that was generally similar to continuous operation. So there's a transitionary period after filter startup that needs to be better evaluated moving forward. When we looked at esterase activity, however, we did see the same trends. We didn't see a notable change in activity after 1 hour of operation or 4 hours of operation. So activity is more variable at startup, but it was similar to the control after 4 hours. Looking at DOC removal, full-scale settled water achieved about 40% reduction. And we don't really see a lot of removal by the full-scale or the control filter through these cold water conditions. And that may be an impact of slowed down biological reactions impacting the removal of DOC by biological pathways. However, what we do see is a huge variability between samples collected 1 hour after startup and samples collected 4 hours after startup in the experimental filter. You can see that on average, we actually achieved a negative reduction or an increase in DOC, whether that's material still coming through the backwash or potentially biomass or something else sloughing off of the filter media, we're currently unclear, but we did on average see impaired removal of DOC compared to samples collected at 4 hours. And we didn't see any statistical difference or any difference between samples collected at steady state from the experimental, full scale, or control filters. Similarly, the chlorinated pilot, which received inline coagulation at pilot, saw similar performance with respect to DOC. When we look at THM formation potential reduction, we see much better, we see a very similar trend. Water quality after 1 hour is slightly worse than settled water, but that comes back up to approximately the same removal after 4 hours and is similar to the control statistically. And we also note here that there's an improvement in treatment following filtration, which alludes to the premise that there might be some biological degradation of these DBP precursors. We saw less than a few percent reduction of bulk organics, but we're seeing roughly 15 to 20% reductions of THM precursors through filtration, which may be associated with biological treatment. And similar results were seen through the chlorinated pilot. So there were lower THM formation potential control following startup, but ultimately at steady state, all of the filters achieved similar removal. So to summarize cold water testing, shutdown up to 96 hours didn't impact biomass density or enzyme activity. So the biological community in all of the filters was similar despite shutdowns of up to 96 hours, and it didn't impact organics reduction at steady state. However, it is important to note that we achieve steady state within 4 hours. And in a pilot study like this, it's important to contextualize these results and say, we can avoid this at full scale if we prevent simultaneous startup of filters. So if we stagger the startup of filters from more than 4 hours, there's only ever one filter that's going through this potentially impacted water quality. And future studies that we're going to look at will evaluate filter to waste to see how long that study or how long of a period that requires to reach steady state. And ultimately, similar treatment was provided during warm and cold water conditions, and that likely plays into the fact that they can optimize coag dose to improve physical and chemical removal and combine that with biological treatment. So to summarize, elimination of pre-chlorination resulted in biological acclimation of the filters. Biofilter shutdown in warm and cold water didn't impair treatment performance, and some improvements were observed, particularly with respect to production and UFRV. And for this, especially biological acclimation, enzyme activity is a preferred monitoring parameter because it tells you what the biomass is capable of doing instead of just how much is there. And we often refer to this as a room full of students. If you put 10 students in a room with 10 pizzas, you don't necessarily know how much pizza they're going to eat, but you could measure just how much is eaten by the number of students. So it's hard to predict based on the number of bacteria, but it's easier to predict performance based on the activity or the degradation itself. Next steps, we'd like to evaluate enzyme activity for process control, see if we can find a way to optimize filter performance based on enzyme activity, potentially using it to optimize filter to waste or as a backwash trigger. We'd also like to look at alternative media for improved biodegradation, looking at GAC as it's been known to provide some benefit to biodegradation in terms of an adsorption or biological regeneration of adsorption sites. And finally, substrate or nutrient supplementation. This is a relatively nutrient limited water source, low carbon, low nitrogen, low phosphorus loadings. So perhaps there's some potential benefit to adding some of those. And I have to give a big thanks again to Eugene, as well as the Water Research Foundation, for doing a lot of this work. Eugene's been instrumental in getting all of this organized at Pilot. I'd love to live there, but being in Toronto is certainly a challenge and learning point to organizing a project 3,000 miles away, and the Water Research Foundation for providing funding. And at that point, I'd like to ask if there's any questions, and you can also feel free to reach out via email if anything comes up after the presentation.
Thanks, Mike. Please type in your questions if you have them. In the meantime, I was curious, I saw several graphs on the DOC, TOC reduction. And it appeared that there wasn't necessarily a improvement in TOC, DOC reduction by going to biofiltration. Can you talk a little bit more about that?
Yeah, and that's certainly been interesting. That's a primary driver for a lot of facilities going to biofiltration is improved organics reduction. And we did see a little bit, maybe 5 to 10% during warm water conditions, but we really didn't see very much following the start of the cold water testing. And I think part of that is optimization of physical chemical treatment. So there's just not a lot of available substrate there. If we think of the amount of biologically available organic carbon, when we're talking with 1 milligram, starting at 1 milligram per liter, it's perhaps on a function of like 0.05 to 0.1 milligrams per liter that might be biologically available. And if that's removed through coag and flocculation and sedimentation, it's just not even available to the microorganisms to degrade. So DOC may just be too much of a bulk parameter to evaluate organics removal.
Yeah, fair enough. Thanks for answering that. And then the only other question I had was around the UFRV question. Is there any theories about what mechanism letting the filter sit for a number of hours or days after backwash, why that would improve UFRV?
I have no idea. The operators at the plant seem to have a pretty good understanding that it was going to happen, but I don't think we've put forth any hypothesis other than it allows the filters to kind of just sit and stagnate for a little bit and then reacclimate, or I guess resettle into their optimal condition instead of getting loaded right away. Honestly, I have no idea, but I think it's really interesting because if that's something that is potentially universally applicable, that you let a filter sit for 12 hours and get some huge benefit to UFRV, that could be huge for a lot of plants, but I don't see it being a universal truth. I think it's something with something at this particular facility.
Yeah. Yeah, I found that quite interesting. It was a staggering increase too. It was almost 200%.
It was crazy. It was really surprising to see that, and they see it at full scale all the time. They have the data to show that at full scale. So it's something that they've observed for decades now, and they're just on to something that I would never have thought.
Well, that's great. All right. Thanks again, Mike.
Excellent. Thank you very much, Josh.
And we'll move on to Alex's presentation.
Okay. Let's see. I think you can see it now, yeah?
Yep, looks good.
Great.
Go ahead and take it away, Alex.
Okay, great. Thanks, Josh. Well, we appreciate everybody being here today. I appreciate being able to be one of the speakers. I think these are a lot of great talks. Just to kind of recap where I've seen we've been today. Lee, you kicked us off with talking a lot about groundwater, of course. Adam, you started to introduce us to ozone biofiltration, but that was with GAC and talking a lot about GAC impacts and benefits. Michael, your last presentation, no ozone, but anthracite biological filtration, right? So just to kind of now let everybody know what we're moving into here is an ozone enhanced biological filtration of a surface water. So this work was done at San Francisco Public Utility Commission's, the SFPUC's Harry Tracy Water Treatment Plant. And it's want to also thank my co-authors, Jackie, who's the process manager there at the treatment plant, Carlos and Bianca, who are technicians at the plant. And they did a lot of, or all the legwork for the data you're going to see here today. And Virpi, my coworker here at Confluence, who was our data magician. So thanks, Virpi. Let's see, as we move into the talk, where did the project come from? So I was able to complete a water quality strategic plan for the PUC back in 2016. It identified many things that could help boost the water quality division's, rigorous monitoring of maintaining water quality across the system. And of that, one of the outcomes was to look at biofiltration at the Harry Tracy plant. And so that's kind of where this project got kicked off. It's not something they were doing. It was operating in the background, and they wanted to know really what is it doing, how can we monitor it into the future and be able to understand it a bit better. So that's kind of like the kickoff into how we got here. What I'm going to go through in the talk are a little bit of background and some biofiltration concepts, some ozone biofiltration concepts, and then get into the operations and monitoring data that kind of was the background of the facility that was being monitored, the Harry Tracy plant. And then, of course, the results and findings of the monitoring program. So some of the backgrounds and concepts. The PUC operates a very large system. So again, we're not talking, we're talking about Northern California here, of course. It's a system that supplies more than 2.5 million customers and has a varied portfolio of unfiltered surface water supply, as well as filtered surface water supply, groundwater as well. They have roughly 240 MGD demand across their system, and about 85% of their system is unfiltered from the Hetch Hetchy, the eastern Sierra Nevada mountains that you see on the right-hand side of your screen. The red line is that transmission and conveyance system that brings water westward into their service area. They have many miles of pipes and tunnels, you can see in the middle part of the text there. And at the Harry Tracy water treatment plant on the far left, it's kind of an endpoint to their conveyance system and what treats water into the proper San Francisco city area. So basically, Harry Tracy plant is the sole source of supply for city of San Francisco. And it is their only ozone facility, but it treats both the Hetch Hetchy water and a local reservoir. And so what does that mean? So let's look at the next slide. So this vertical process flow that you see on the right-hand side is everything that happens prior to getting to the Harry Tracy plant. I thought it was important just to kind of show this, what was going on. There's a lot of tunnels, of course, a lot of pipelines, but you see the orange boxes there. There's a bit of treatment as well. There's pH, alkalinity, UV, fluoride, chlorine, and ammonia treatment, because a lot of that conveyance is unfiltered water that actually goes out, of course, in the distribution system. But prior, at the very bottom of that diagram there, you'll see it going into a couple reservoirs. So prior going into reservoirs, which then feeds Harry Tracy water treatment plant, there's a dechlorination step of that supply, of that unfiltered supply, and it is what supports also that local and catchment reservoir water that feeds Harry Tracy. So there's the big picture of where all this water is coming from. Now at the Harry Tracy plant, here's the process flow diagram, a simplified one for what happens there. So from the reservoir, moving vertically downward, you'll see ozonation, a flash mix, flocculation. It's a direct filtration plant, so there's no settling before the filters. And then chlorine and then chloramines are established before the distribution system. They're a chloraminated distribution system. Throughout coagulation, I think it's important to note here, you'll see in the bullets that there's about 1 milligram per liter of ferric chloride that's used for coagulation. That's their coagulant. They use a little bit of polymer, and they maintain alkalinity, 45 milligram per liter for treatment. So that's kind of sets the stage for where we're at with Harry Tracy. Now I have a couple slides, just a little bit on biofiltration, ozone biofiltration background. So what are we talking about? So ozone enhanced biofiltration typically operates in the background at many treatment plants. It's a tool that helps stabilize, as you heard in a couple of the previous talks, it helps stabilize the bioactivity before the distribution system, so you're not using your distribution system as a bioreactor, is the hope. Some of the impetus of the project is, like, how do we know what events, what operating events, what water quality events impact the filter and its efficiency, which kind of led to the work here. And we tried to base this establishment of this monitoring program on a lot of research and work that I've been involved in the past. And you see kind of a graph here showing some of the results from past publications, where we've been able to, and a lot of facilities now use different parameters, such as what's shown here, carboxylic acids, some low molecular weight compounds that are biodegradable and can be monitored through an IC chemistry method. But you see the loops, the peaks and the valleys of those curves showing how biofiltration efficiency hits a hopeful goal after a steady state, then maybe drops off after a filter media is replaced or operations changes occur, and then you can see it coming back. And I just kind of wanted to show that background graph as an example of kind of what the PUC is hoping to at least achieve at the establishment of this monitoring program, to be able to see what their filters are doing and what might impact them, what might impact the efficiency of those filters, and what does that mean really for them, what things should they monitor. So based on this past work, we did want to look at carboxylic acids. We did want to see if that horizontal line in the graph, which is showing like a 70% reduction of carboxylic acids through biofiltration, if that could be achieved at Harry Tracy, is that normal? And kind of go from there and see if there's other things we can use to monitor the filters. So, and if I can change the slide, here we go. And not only from that past work, we looked at some of the recent studies that have been published. For one, at the very top of the left screen there's publications showing that, people don't really know what biofiltration does when you send out a survey. Even operators at the treatment plants, I don't know what it does. It's just kind of there, and we just don't chlorinate the filters. And so there's, of course, this building of understanding and knowledge and education that this study was helping bring to the PUC, because they were in the same boat as the typical facility, which doesn't monitor their biofilters. There's engineered biofiltration studies. This was not one of them, and we'll talk a little bit more about that later. But there's studies that show by adding nutrients, by adding specific low doses of oxidants, you could maybe fine tune how the filter operates, the different efficiencies, how to overcome detriments to operation and things. So that's something that's being folded into this work, hopefully into the future for them. But we didn't just jump into running an engineered study on this project. And then also the last point there at the bottom, there has been a monitoring manual that's been developed for recommending specific parameters that could be used and helpful for facilities to monitor their ozone biofiltration process. And that was used, of course, to glean some insight and to improve our study as well. So for project setup, we wanted to basically wanted to help Harry Tracy see how their biofilters were operating. Again, they hadn't been monitoring them for biological activity. And we wanted to set the foundation for future work for hopefully optimization and maybe further enhanced studies, maybe some engineered principles and such. But this first study was the implementation of monitoring to help fine-tune what parameters helped, what parameters maybe didn't help, which parameters were very difficult to collect and maybe costly, and were there surrogates that we could use then by collecting a wide range of parameters. Could we see surrogate measures that could be replace maybe some of those more costly parameters to monitor? So it was really a high-level first step with a lot of monitoring to get a good foundation laid for further work, for a second phase of work really to be done. So you see some of the questions we're hoping to even look into answering. What's happening at steady state performance? What is the biofilter doing? How can we lower maybe cost of operation and optimize future monitoring? These are all questions that are hoping to be answered not only by this study, but build on work to this work at the PUC. So in terms of background operating and monitoring information at the treatment plant, we did this project over about 15 months back in 2018, 2019. And you see the process flow diagram again on the right-hand side of the screen. Those stars indicate where we were monitoring, more specifically, information coming from the plant, as well as water quality change and such through the process. So you see it at the top there, the ozone process, before and after ozonation, the coagulation process, before and after coagulation, and you'll see that term AWWA on the right-hand side of your screen. That's how that's what they call their flash mix and flocculation channel, the applied water channel before going to filtration. You might see that acronym later on. We monitored the filtration process, of course, and before and after chlorine contact and into the distribution system as well. And we looked at a lot of these parameters on the left on the text here. Chlorine residual demand decay. We did look at oxygen ORP, a lot of metals, microbials, organics, and others. And we also had one of the filters with some dedicated in-depth filter profile taps, which helped us see what was happening through the depth of a couple of filters. So that's where, that's how we, let's see, did I skip one? There we go. That's how we started the program. I'm going to get into a couple slides showing some general conditions. I'll just kind of orient you to the figure on the right. You see a couple y-axes. On the left here is temperature and pH, and on the right is the flow rate. So the blue bars, vertically blue bars, show a couple times when the plant was actually shut down in February and October of 2018. So we wanted to see if those could show us anything in the data, of course. So we tried to pay attention to that. The blue line you'll see is the flow rate, range between 30 and 100 mgd, and that orange line kind of shows how warm, basically, well, it does show how warm the water temperature is there at the PUC going into Harry Tracy. Always above 12 degrees C and about to 20 degrees C. So it doesn't get very cold in that water through treatment. Kind of building on this graph, just kind of adding a couple things. Those orange circles show the TOC, which range roughly between 2 to 3 milligrams per liter. So there's quite a bit of TOC coming into the water. And the orange line you see kind of at the bottom there is the turbidity. It was always below 2 NTU during the project. And again, for the Hetch Hetchy, that's pretty normal. And because it's being used as an unfiltered water for their distribution system, and a lot of their distribution system, it's operated at a low turbidity level. So that a little bit of background on water quality. One last slide here on some of the background water quality, showing some ozone data being added onto here. So the blue line is the ozone dose. That solid blue line, you'll see some gaps in the data there because of some different things that were going on in the program. But the ozone dose range from 0.7 to 2.2 milligram per liter. You'll see the blue squares, which show the ozone to TOC ratio, which basically at a multiplied times 10, so we can get it on to the graph there. The ozone to TOC ratio was basically kept at about 0.5 milligrams per liter on average. So in other words, for every milligram per liter of TOC that was present, the ozone dose was about half of that on average across the program. So that's kind of typical for ozone biological treatment plants where your ozone dose is really tied to your TOC level coming in. And for them, it's at about a half ratio of 0.5 based on the TOC. So another thing just to point out here, which is something that's a little bit different in the Pacific Northwest, is in California and at Harry Tracy Water Treatment Plant, they're allowed to achieve Giardian activation credit with ozone, something that is changing, and I know that permitting is changing in Oregon and such, but it's something that's fairly new up here, where Giardian activation credit was basically supposed to be achieved after filtration. The ozone operating conditions, everything was tied at the Harry Tracy plant to achieving Giardian activation credit with ozone, and that's how the ozone system was operated. throughout this study. One last slide with a lot of operating data on it. I'm not going to go into a lot of detail here. You can kind of see the shutdown periods again, and there's a lot of dashes and dots and such here, but I wanted to at least just emphasize that part of the sampling conditions for the project was that we sampled the filters consistently across the whole program. So for example, the triangles that you see there are almost in a horizontal line from left to right. That triangle indicates the run time of the filter, which you kind of see on the left to be about almost 20 hours. That run time of the filter was kept the same was when we sampled the filters. And the circles in the bottom are basically the head loss of the two filters that we sampled, which was roughly about 8 feet each time we sampled. And we tried to be consistent across the year to just monitor just the consistent period in time of the filters operating. Last thing at the top, which I'm not going to go into a bit of detail on, but shows the total runtime. Those dashed lines are the total runtime of the filters, and those kind of decrease from left to right. That's basically based on, that was because of operating conditions and how the filters were taken in and out of service later into the year and at the beginning of 2019 compared to the beginning of 2018. So it was an operating condition at the plant, not necessarily something that was happening because of a biological impact on the filters. These filters have been operating biologically for many years, several years before this study started. And so it's not that biofiltration started at the beginning of the study, and so that decline there isn't because of something changing biologically actually, which is one of the findings that we tried to pay attention to during the work. So as we move forward, we're going to talk about some results and findings here, and just to let you know that this data here, there's two examples of the data. There's scatter plots on the left, and there is box and whisker statistics on the right. So those are two kind of formats you're going to be seeing. So the scatter plots show data over time from left to right across the program at different locations, and the statistics on the right show the statistical breakdown of the data for whatever parameter we're looking at the different locations. You can see on the raw water, ozonated water, the AWC, when we have water for that, the applied water channel, and then the different filter, not only the depths, so we have filter information for 2 filters, 5 and 7 at 24-inch, 48-inch, as well as the effluent and their distribution system. So I just wanted to orient you on those graphs. So we have a lot of graphs just to kind of go through. So one thing we looked at, and one thing that they wanted to pay attention to, was iron and manganese. So we looked at oxidative state, ORP, oxidation reduction potential. It's the oxidative state, you can see in the scatter plot in the top graph there. Let's see, the scatter plot in the top graph. The ORP for all the different areas range from 100 to even higher millivolts. Kind of as a reference, when DO is present and you have an unchlorinated water, you might have an ORP of about 100. After ozone, this bumps up to about 300 or so. If you have a chloraminated water, because of the chlorine oxidation capacity from chloramines, you might be at about a 400 millivolts ORP and about a 600 if you were free chlorinated. So those are just general. Those, of course, all can range, but that's just a general snapshot, an idea of what different ORP levels might be for different treatment conditions. And why is this important? Well, we wanted to understand any ORP changes going on at the filters and such because of the potential for iron and manganese change and release. And if there was iron and manganese being oxidized through treatment, being captured by the filters and possibly oxidized onto the filters, if there was an ORP change, should they worry about the change in the capacity for the filter to hold that oxidized level of iron and manganese, and would it dump that iron and manganese? So you can see oxygen level was pretty high, especially after ozonation. It's super saturated throughout the whole treatment train. And the bottom left there, the ORP is around 250 on average, those median dots across the whole treatment, and goes up a bit after chloramination into the system. So what does that mean for iron and manganese? Well, we looked at iron, and we see here on the left of that graph the raw water, and going onto the filters, those two bars that are high there, filter 5 and filter 7, about 24-inch iron levels going onto the filters, and then being captured by the filters. You see iron very low. There's excellent capture and removal of iron. Remember, they have ferric chloride, the iron-based coagulant, going through treatment. And so there's basically very good capture of the iron going through the filters before the distribution system. And then the same thing with manganese. Let's look at the left graph first. So this shows the same box and whisker graph, where we have basically a high level of manganese during treatment. Ferric chloride is notorious for having a bit of manganese contamination in it. So they're basically dosing manganese into the treatment plant while using ferric chloride. You can see that increasing from the raw water, and then through filtration, you see a little bit of capture on that upper level of the filters, the 24-inch depths, and then those dots at the bottom of the screen are the lower level of the filters where manganese is being captured by the filter. One thing we try to look at on the right-hand side there, the top and bottom graphs are, is the manganese speciation changing between dissolved and particulate through different levels of ORP. We didn't really see that, so I wanted to just throw that there to show that we were trying to look into that. But what we do think was happening on these filters was either one of two things. One is either the iron and manganese is shifting into a particulate state and being removed by the filters as a particulate, or they're being oxidized onto the filter media because of the high ORP levels that are there. And then once you get into the filters, you have a very high surface area because you don't just have 4 walls and a basin anymore. You have that the filter media everywhere, and the iron and manganese is being oxidized possibly onto the filter media. So we want to pay attention to that, and if there's any changes in ORP, does that iron and manganese come off, or is it a particulate that's being removed and being pushed into backwash? That's something that needs to be studied a little bit more, and we'll talk about that more later. So before getting into the biomass, microbial indicators, and organics, just a quick check on kind of why would we look at each of those and what do they have to do with biofiltration. So biomass are the guys that are doing the activity. Those are either the heterotrophic bacteria. It's possible that coliforms could be established on the biofilters, and ATPs can be measured as a surrogate. It's an indirect surrogate for biomass, and you saw that in the last presentation from Michael, ATP being monitored. Organic matter can be monitored. That could be the TOC, the dissolved organic carbon from the TOC, or other surrogates such as UB254 to look at the organics that are coming through the system. And then what are the biodegradable organics, that fraction of the organics that are available and are biodegradable for the biomass, the cells to use as kind of a food for them. Those could be AOC, assimilable organic carbon, BDOC. You maybe have seen some of these terms. And I mentioned carboxylic acids, I abbreviate as CBXA for short. Some of these compounds to kind of monitor the bioactivity and the efficiency of the biomass, reducing the biodegradable organic matter. So those are some of the things we're going to be looking at in the few next slides. So as a setting point, we took a look at, ATP levels of onto the media at the filter. So we have filter 5 in this table we have here. In the middle column is filter 5 levels, the top 2 rows at the treatment plant. Filter 7 levels of ATP from the filter media sampled at the Harry Tracy plant, those top 2 rows, showed that they were about colonized, the filter media is colonized about 10 to the 5 picograms per gram of media throughout that filter. We wanted to compare that to the literature, just to kind of see where we sat. And so that bottom row of the table corresponds to the figure on the bottom left, where the study published by Hooper, which I referenced earlier about the biofiltration monitoring methods, showed that across a bunch of plants in the US that they were monitoring, they ranged from 10 to the 3 to 10 to the 7 picograms per gram of filter media ATP measurements. And we were kind of right there in the middle, 10 to the 5. So we felt like, well, that compares well to the media, to the literature. And so it was a kind of a nice benchmark to kind of see what level of the filter media was colonized compared to other places across the country. We also looked at some different microbial indicators that I mentioned earlier. We looked at coliforms in the middle top there, different levels across the treatment plant, where we wanted to know if coliforms were being produced and established in the filters. You know, there's no chlorine residual there. Some biological filters in the past, depending on how they're managed operationally, can get a bit, how do I want to say it, producing things that you might not want to keep around, even higher organisms such as worms and such. So we want to look at coliforms. You can see across, there's coliform levels are very low across the filters, which was a nice thing to see. On the bottom left, we looked at ATP in the liquid stream, as well as the previous graph showed looking at ATP based on measuring filtered media mass of biofilm. This looks at bacteria levels going through the process in the liquid stream. And you can see it kind of bouncing around there, but between 1 and 10 units or a little higher than that throughout the filters, and then dropping quite a bit once you get to chlorination and out into the distribution system, which makes sense because you're adding chlorine and knocking back that microbial load. And on the right-hand side, it just kind of shows the scatter over time of ATP across the whole study, basically. So this was kind of nice. It told us that there was no problems, I suppose. There's no overgrowth of coliform bacteria. There was pretty low levels of any nuisance organisms that we saw. We also looked at chlorine demand and decay. These are 3 snapshots of chlorine demand decay that were captured throughout the study from left to right: August 2018, December 2018, March 2019. The one thing that, again, let's step back, this was establishing of a monitoring program. We did not alter treatment performance of the treatment plant, so we didn't have a chlorinated filter to compare to see if the biological filters were performing better than if the filters were chlorinated or not. We were just studying how are the biological filters performing. And what these graphs basically show is that the filtration process is definitely providing a great benefit to improving or reducing not only the demand of chlorine, but the decay rate of chlorine. It's reduced demand roughly between a couple tenths of milligram per liter compared to before filtration, before the biological filters. And the decay rate slowed when compared to the CDD, the chlorine demand decay before filtration, about 5 to 10 hours when you get down to a terminal residual of, let's say, 0.2 milligrams per liter. So it was definitely showing a benefit to chlorine demand and decay. Again, we didn't have a non-biological comparison, but this was a nice thing for the PUC to see and to think about for building future monitoring changes to the monitoring program, to try to investigate how that CDD can be improved possibly. Now, as a quick reminder, before we look at the organics, I wanted to show this box diagram here, just to kind of reorient ourselves as to what we're talking about in terms of organics. So when we talk about at the very top there, natural organic matter, the broad range of organic matter that can come into a treatment plant after it passages into waterways, coming to our facilities, that splits into TOC, total organic carbon, and other unknown organics. The TOC measurement that we have basically represents about 50% of natural organic matter. That's just a generic idea to what that TOC is actually measuring. Within TOC, there's dissolved organic carbon, DOC, and particulate organic carbon. That's aside, and the DOC can be a range of 40, 50, 60% of the TOC, all the way up to 100% of the TOC, depending on where you are in the treatment stage and what the characteristics of your source water are. And then underneath the DOC there, you'll see after oxidative treatment, some of that DOC can actually be moved into biodegradable organic matter, BOM. And how do we monitor that? And that's kind of where the crux of the program here is, and what folks try to hone in on. Some of those monitoring characteristics can be very difficult and very costly. I have two examples down there at the bottom: AOC and BDOC, assimilable organic carbon and biodegradable organic carbon. Well-established monitoring parameters that can be monitored, well-established laboratory methods have been used for years, but they're difficult for some to implement because they're very laboratory time-intensive, staff-intensive, and so very costly to implement AOC and BDOC. So what we picked in this study, you'll see in the little boxes, the darker green boxes, CBXA, carboxylic acids, to monitor for filter performance. And you can kind of see the reason why I have them there in the boxes is they actually show just a small portion. If you measured carboxylic acids directly, you're just seeing actually just a small portion of the AOC, which is then in turn a small portion of the BOM, which in turn is a small portion of the DOC. But the nice thing about this is studies have shown that the relative composition of these compounds are the same. So if you were to get roughly 50% removal of carboxylic acids, you should be able to expect roughly 50% removal of AOC and such. So relatively similar in terms of how to monitor plant performance, but if you can target some of these different compounds and hopefully they're a little easier to measure, maybe it just reduces your loading of work a little bit. So let's get into the data. So TOC we monitored, you'll see on the left-hand side just the different locations throughout the treatment plant, the orange and blue happening before filtration, and then the dark spots are basically the filtration spots. So you see roughly a 20% reduction of TOC going through the filters. You'll see then the statistics on the right-hand side, a little bit of a snapshot per location. The DOC to TOC ratio, so how much of the total TOC is actually DOC. So before filtration, you'll see it's roughly 90%, but it ranges between 70 to 100% of the TOC is actually the DOC. And on the right-hand side, once you go through filtration, it's mostly all DOC. It goes up to 95, 98% of the TOC is DOC. So it's almost all dissolved organics, which makes sense. We're removing the particulates and we're going through filtration. And so it's all dissolved organic carbon by the time we get through the filters. And so as dissolved organic carbon, that's the part that could be acted on by and is made available to those microorganisms through the ozonation process. And so you'll see on the top graph here, again, a kind of a little bit of a repeat of some of the DOC data at the very top, the applied water channel and what's going on to the filters. But at the very bottom of that time graph, you'll see what we calculated as biodegradable organic carbon. We kind of made up our own calculation. Rather than putting in a laboratory method of monitoring BDOC, we calculated the removal of dissolved organic carbon across the filters at the different depths and such to kind of use that as almost a surrogate of biodegradable organic carbon. If the DOC is removed from the filter, it's being removed through that biological process. We felt we could kind of say quite confidently. So you can see roughly about 0.5 milligram per liter. We're reaching about November, December of 2018, removal of BDOC on that time scale graph. The bottom box and whiskers show DOC being removed at different levels of the filter. So we're seeing about equal removal of DOC through the different depth levels. So that first to the left, those first three bars are for filter 5, the second three bars are filter 7. You'll see about 5% removal in the first depth, 24-inch, another 5% removal up to being a little bit more than 10%, going to the 48-inch, and by the effluent of the filter, we get about a 15% removal total. So about 5, 5, and 5% as we move through the filter. So anyway, that's what that one is showing. for BDOC, we also looked at that measurement of carboxylic acids, right? So for carboxylic acids, it's again an IC chemistry method, which looks directly at this low molecular weight compound that's being produced by when ozone breaks down organic matter. So it's very low. If you look in the top graph, the time scale graph, that orange line, that solid orange line is the raw water. It's very low on the raw water, but then when you ozonate, the black and blue lines at the very top of that graph show how it just jumps up, right? So you're producing a lot of PDOC as measured, or BOM as measured by carboxylic acids. And we wanted to see, of course, the efficiency of removal. So that top graph is the calculations based on that top graph show at the very bottom graph that were the horizontal line, which is a roughly 75% removal. We're able to achieve that through the study, except for a few data points on the left there. So from November 2018 and after is a nice stable above 75% removal of the produced biodegradable organic carbon as measured by carboxylic acids. Some of the things that happened before, we actually think there were some data challenges, but also, excuse me, we tried to look at some of the shutdown periods. You might remember before was February 2018 and October of 2018, where there were some shutdown periods. And it's possible some of those data on the left after February 2018 were because of that initial shutdown of the filters for about a month in February. And it took some time to recover, but it was a little difficult to tell because of the spotty data we had at that time. But then you look after October, maybe it's because the warmer water temperature, those filters just came right to biological activity right after that October shutdown.
Hey,
So,
Alex, we're pretty close to over time here, so just FYI.
okay. I'll just wrap it up. So we tried to look at surrogates for carboxylic acids because they had to send those labs out. There's some possible surrogates, and we're doing more work on that to identify those. But you know, just a lot more data there to show it to you. But just to wrap up, there's no indication the biofilters were experiencing operational deficiencies, which is nice. This kicked off some great monitoring for them. It compared well with the literature, and there's things that they're carrying on in the future to try to identify if the filters are removing manganese, removing iron. They want to look at emerging pathogens, such as could biofilters be a harbor for some of these pathogens, and kind of optimizing this monitoring into the future. Quick thank you again to the PUC. Brown and Caldwell was the main contractor that we were able to do this work through. So Lynn and Aaron did some QC reviews for us. And also big thanks to Eurofins. Wanted to say they did the analytical work for carboxylic acids. So that's all. Thank you. Sorry about the time, and thanks for letting me come in today.
Thanks, Alex. Appreciate it. If you have any questions, go ahead and type them in. There was one question, Alex, on what a chlorine contact ring is.
Oh, yeah, the picture. So it's just basically an outer ring, and their chlorine contact are circular. So they have chlorine contact going in the outer ring, and then they add ammonia before it goes into an inner ring, and then it heads out into the distribution system. So it's kind of a little bit of a unique design. Yeah.
I see. Yeah, that is quite unique. Any other questions from the crowd? Looks like there's not. So we'll take a break until about 11 o'clock, and we'll rejoin then with our next and final two presentations. Thanks again, Alex.
Thanks, guys.
Hey, Milt, you want to
Yes. Can you hear me?
shot, see if it's working? Yeah, I can hear you.
Okay. What was your question?
Oh, I was just going to make sure your audio is working okay.
Okay.
It is. That's good.
I was getting a little worried when I signed in, and then it asked me after I was already on for the password, and I punched the password in and clicked on sign in, and nothing happened.
No, no. Well, I'm glad you made it.
Yeah.
All right, let's get rolling again. We have one last poll that we'll conduct. I'm launching it now. What level of taste and odor concern is there for utility? As we're talking about ozone, biological filtration, often there's a taste and odor component when we're treating for those compounds using ozone and biofiltration. So I figured we'd get a sense of who has taste and odor concerns with their utilities, if any. So none, low, medium, high is what we're looking for here. Looks like most folks have pretty good water, low to no taste and odors, which is great. But a few folks that have medium and high. Give folks another 20 seconds or so to respond. All right, I'll share these results, and then Milt, you can go ahead and take over. I'll stop sharing.
Let's see. Okay, this is a project we did recently for the city of
Hey, Milt?
Sacramento. Yes.
Sorry, before you go on, I'm actually going to remember to read your bio.
Okay.
Been pretty bad at that today, but Milt Larson has served as a project manager and process treatment lead on numerous water quality evaluations, corrosion control, water distribution, and treatment projects. Milt has evaluated and designed treatment facilities for numerous groundwater contaminants, including PFAS, PCE, NDMA, DBCP, hydrogen sulfide, iron, manganese, arsenic, and ammonia. Milt is a member of the Pacific Northwest Section's Water Treatment Committee and AWWA Inorganic Contaminants Research Committee, Corrosion Control Committee, and chairs the AWWA Standards Committee on Scale and Corrosion Control Chemicals. He's a life member of AWWA and participated in the preparation of AWWA Manual of Practice M64, Aeration and Gas Stripping, first edition, and M58, Internal Corrosion Control and Water Distribution Systems, fourth edition. All right, now go ahead, Milt.
Okay.
Take it away.
This is a project for the city of Sacramento where we're rehabbing filters 9 through 16. Originally, Doug Henderson was scheduled to give this presentation, but he decided it was time to retire. So just briefly, an outline, we're going to just an overview of the city's water system, the city's goals for the rehabbing the EA Fairburn water treatment plant, some of the condition and performance challenges, some of the process for the construction rehabilitation, and the filter activation and performance testing. A little bit of background on Sacramento's water system. They've got 2 surface water treatment plants. The Fairburn treatment plant's rated 100 MGD based on 8 of the 16 filters operating on the American River, and the Sacramento River water treatment plant, 160 MGD. They serve a little bit over 500,000 people. They also have 23 active wells, 1,700 miles of water mains, and it's generally flat with a single pressure system. A little bit of background on the project was to replace undersized median to restore the filter loading rate. Filters 9 through 16 were installed in 2006, and it turns out that the media that was installed in the filters was incorrectly sized, didn't meet the design requirements, and there was a lawsuit over that, and the city ended up getting a fair amount of money back. And so we're getting about 3.5 to 4 gallons per minute per square foot, and the original design was 5.1 gallons per minute per square foot, and they're planning on testing the facility up to 6.3 to see if they can get 100 million gallons a day through those 8 filters. The water is pretty soft, and they're having deterioration of the concrete structures, and so they wanted to protect them from further deterioration and demonstrate testing that they could get up to 100 million gallons a day through those filters. And so they're going to use this work to determine what the facility capacity is, and then also look at what they need to do to upgrade or replace the 1964 system, which is in pretty sad shape. The source of the water is the American River with pH of 6.8 to 7.4, and it's quite soft with a typical hardness range of about 43 to 36 milligrams per, average is about 43 milligrams per liter. They've got 2 trains in the original 64 plant, and then 2 trains for the 2006 plant. It's a typical conventional water treatment plant with rapid exflocculation, sedimentation, filtration, followed by disinfection, corrosion control, and fluoridation. So the 2 trains are right here. So there's the 64 plant here with the filters from the 64 plant, and the 2006 plant there. And then just general layout of their solids handling as well. So the design criteria for the system, they've got 8 filters for the 64 plant and 8 filters for the 2006 plant. What main differences are: 64 plant had slightly larger filter area, and they were using garnet, sand, and anthracite, whereas the 2006 plant is silica sand and anthracite. And the design filter loading for the 64 plant's 3 gallons per minute per square foot compared to 5.1 gallons per minute per square foot for the 2006 plant. So as I indicated, the media that was installed in 2006 was undersized, and they prevented the filters from operating at the design loading rate. And the original 1964 plant filters have become unusable after degradation of equipment and concrete structural damage. And so they're looking at rehabbing the 2006 plant to see if they could meet or exceed the original design criteria. So after 14 years of operation, they were seeing early stages of concrete deterioration in the 2006 structures. And in comparison, they were the 64 plant had severe concrete aggregate exposure after 40 years of operation. So they bid the job, and they intended to start the project in 2017. They didn't actually start until May of 2018 because of a bid protest. The low bidder was thrown out. The second bidder, which filed the protest, ended up getting the job, and so he started in May of 2018. And then there was some additional delays, and so they finally they plan to complete the work in December 2016, but they finally completed it December 2019. And due to the modified time frame, project conditions were updated to reflect new concerns. They would only allow the contractor to take 2 filters off at any time. And under certain cases, they'd have to bring them, well, once they took them offline, they were out until they came back. They restricted the contractor's operation from Monday through Friday from 8 a.m. to 3 p.m. And they had to contain everything that was on the upper deck of the filters. They didn't allow them to store materials in the upper deck, and they had to fully dechlorinate all discharged water. And there was a limitation when they backwash the filters that they could discharge no more than 500 GPM, which is the maximum the city could, the water treatment plant could then discharge to the sewer. So during setup, they determined the laydown areas, storage areas, and construction areas in the plant. They required them to have plastic covering over the filters that were being sandblasted. Had to have they used sandbags to seal off the air tarps around the tarping, and monitored and covered all areas. And then the contractor was required to review a video on chlorine safety and then sign off and before beginning work. And they had to update their personal protective equipment requirements and provide access to SDS sheets. So they, like I said, they covered the filter deck openings and they double contained the media, and they had to protect the facilities from impacting the water quality from overspray. So the first step after they set up and prepped everything was to remove the media. They had sufficient bins on site for material offloading. They used a backer truck for removing the media. They had to minimize moisture in the filter media, and the existing media they found out once they got into the taking the media out was not as what they expected. There was supposed to be 12 inches of sand, and they found out they actually had 30 inches of sand, and they were excuse me, they actually had 18 inches of sand. They were supposed to have 30 inches of anthracite, and they found out they actually had 25 inches of anthracite. They already knew that the media was incorrectly sized. The contractor was responsible for protecting filter nozzles that were installed from damage. But then they also found out that their supposed as-built drawings were incorrect. There was a number of things they found in filters that wasn't as anticipated, including they found angle irons had been installed around their expansion joints. So when they first started up, it was taking about 4 to 5 days to remove the filter from the media from a filter, and by the time they got it down later on, they were able to reduce that to 2 to 3 days per filter to remove the media. And so they were staging the media on site. They had several areas set aside for unloading media as well as for used media storage. After they took out all the media, prior to working on the coatings, they conducted nozzle tests to identify pre-existing issues. And the contractor was required ahead of time to pre-purchase about 2,000 replacement nozzles. It ended up that they had maybe 50 or 60 nozzles that were broken that had to be replaced. They did find out that they had leakage through their expansion joints, was bypassing the nozzles, and they had somewhat unbalanced flow in some conditions. So they physically checked the condition of each of the nozzles, and then they had to confirm the conditions in the underdrain, including its cleanliness. And they had a number of unexpected findings. They had holes and breaks in the expansion joint material. And they had equipment and parts left behind from the original construction from 2016. They found wood used in the forming in the underdrain section, as well as they found rags and wire left over from wire ties. Some of the materials, like the angle iron that had been installed around the perimeter, found out it was carbon steel rather than stainless steel. That was one of the unusual construction modifications they also found. And then, as indicated, the media didn't meet the original installation requirements, and they found a number of structural cracks in the floor and exposed rebar. So they found in the plenum area an unexpected amount of alum buildup in addition to the other debris that I mentioned previously. They also had areas where the silica sand and anthracite had entered the plenum through broken nozzles. And then they had some anchor bolts that were not stainless steel, they were carbon steel in that area as well. The surface of the concrete inside the fillers, they found that the surface of it had deteriorated quite a bit, and the pH had dropped down to approximately surface pH of 7. And they had areas where they had exposed rebar and cracks. They did some epoxy injection. They had to seal up some water that was intruding and remove expansion joint material. And then they had to address surface anomalies, remove the angle iron, and they had to protect the areas not intended for coating, such as the flumes and such. So they ended up, they evaluated what pressure they needed to use, and they water blasted to remove most of the soft cement material and leave a good aggregate exposed. Protect the fiberglass troughs while they're blasting around it, and then they needed both abrasive and non-abrasive blasting from the floors depending on the condition. And then there were some steel surfaces which they dry blasted with abrasives. Just a couple shots that were taken. One in the center is the floor area where they removed the nozzles and they installed temporary caps before they blasted. So some of the after they finished with blasting, some had repaired the structural cracks and coated the exposed rebar. They ended up having 2 different coating subcontractors. The first coating subcontractor lasted through 2 filters, and then he wanted out. And he was going so slow that the prime contractor wanted him out too. So they switched after the first 2 filters had been recoated, and brought in another coating subcontractor for the last 6. And he seemed to do a bit better job. There was a number of issues that they had in regards to applying the coating. They had to deal with rain, as it's an unusually wet year, and a real problem with off-gassing, which led to a number of pinholes. Then the temperature and sun impacted curing, and then they had some wind issues which impacted their blasting activities as well as the coating, and it caused havoc with their tarping over the filters as well. So after the sandblasting and removal of the material, they ended up applying a parge coating to fill the deep voids. And they'd looked at a couple different top coats. One was a polyurethane top coat, but they finally settled on a plural component epoxy. And so the purpose of it was to separate the corrosive water environment from the concrete surface and prolong the life of the concrete. And they ended up, there was some concerns that the epoxy was in particular exposed to sunlight, would tend to chalk and fade a little bit over time. But that was a choice over the polyurethane top coat. They ended up applying the coatings in the evenings when the temperature was dropping, so that the moisture emission rate from the concrete was not going out, but more there is more sucking in the material into the concrete surface as the temperature dropped. They ended up having to store the parge coating in an area to maintain temporarily cool temperature, and then the plural component epoxy was heated to 180 degrees Fahrenheit. So this is just some shots of the initial parge coating. They needed an experienced applicator, and they were filling the voids before applying the epoxy finish coat. And then they needed to clean up the parge coating before prepping for the epoxy coating. So they used several different methods for applying the parge coating, and then sprayed on the plural component epoxy. And as you can see from this photo, they had significant problems with off-gassing, creating a large number of holidays in the coating, which the contractor had to go back in and repair, which is quite time consuming. And they had more of a problem with the first coating subcontractor. Just had a real devil time trying to minimize the holidays in the coating. And then they had some other issues that the inspectors found during the application of the coating. They had some drips and poor coating around non-uniform surfaces, such as butterfly valve. They had areas where the coating was applied in too thin, and also had a number of areas where the contractor just completely missed the coating areas. And then after they applied the coating, they had to remove the temporary caps. And so they used a rotary cutters to cut around the temporary caps for removing the caps and install the new nozzles. Then they applied the expansion joints within the areas where it needed to be installed, and they reinstalled the angle iron all around the perimeter. Although this time they used stainless steel materials in doing that. And then in the process of reinstalling the nozzles, they ended up having to replace roughly 250 nozzles. The original 50 to 60 that were found to be defective. And then there's a number of them that were broken during installation or removal for the blasting operation and reinstallation. But it was a lot less than originally anticipated. Just some shots of reinstalling the angle iron, installing the expansion joint, and sealing the uncoated areas. So in the underdrain, they had to remove the debris, and they ended up using flushing down the water, as well as using the shop vac for the most part, and then they install the areas, repair gaps as well. And then before installing the media, they ran filled the filters and used the air scour to look to see how the distribution was coming back through the nozzles, as well as how their distribution during backwash as well. So there's some issues with the media installation. The supplier had a lab provide a report prior to delivery, and then the city had a third-party lab upon delivery take samples from the media and run sieve analysis and so forth. And then after the media was installed and scraped, they did a post-installation confirmation. And initially, there was some thought that the contractor might use a crane to install the media. And there were issues around that regarding protection of the nozzles and the channels and media. But the contractor ended up installing all of it by a Venturi inductor. So he just had to provide secondary containment for the hoses, and he did have some complications with pressure loss. And then he had to provide sufficient media for scraping after installation. So the district had, or the city had the philosophy they needed to trust and verify each step of the media installation. So they, as I indicated, they tested media prior to shipment, after it arrived on site, and also after it was installed. So after the sand was installed, they air scoured and backwashed at a rate of about 16 to 18 gallons per minute per square foot. And they went through about 3 backwashes and 1 air scour. And it took them three days of backwashing and scraping to get it to the point that they felt was successful, which they indicated less than 5% of the surface was covered by fines. And then they installed the anthracite, and it took quite a bit more backwashing. It took them about 5 days per filter of backwashing and scraping. And then they considered success once they were getting less than 20 NTUs on the first run and less than 5 NTUs on the third run. So prior to disinfection, they wiped down the walls of chlorine solution, and then they used they chlorinated and provided a minimum 25 parts per million in the underdrain and on the surface filter. And after 15, they had to have a minimum of 15 parts per million in the underdrain and on the surface of the filter after 12 hours of soak. When they initially, on the initial disinfection effort, they failed the BAC-T test. And so they revised their methodology somewhat, changed the disinfection point. And the city was using an 18-hour cold alert test so they could expedite getting the results back to the contractor. And then they flushed after disinfection. And then filtered waste and then returned the filters to service. So just some shots that were taken when they were setting up to install the disinfection process. Now the city had to learn to expect the unexpected. There were a number of supplier issues. The suppliers didn't meet their delivery schedules. In the case of anthracite, the initial anthracite supplier couldn't meet the specification. So he claimed he was providing an upgraded design, and the city had already been through the ringer over having a media that didn't meet specs. So basically, they said no, they stuck to their guns and required the anthracite to meet the required specification. They also had some contamination issues. There were about 4 super sacks of the anthracite that were rejected. They ended up having chunks of anthracite that didn't meet the gradation. Some of them as large as 1.5 inches in diameter. And so they were tossed. They also had unmarked and unexpected deliveries. There were some deliveries that showed up with no markings on it to indicate what lot they came from. And some showed up at unexpected times. And the city, the lab was initially used for testing on site. They didn't, when they ran the initial sieve analysis, they didn't use the appropriate AWWA sieves. And so the results we got back from the lab indicated they didn't meet the effective size requirements or the uniformity coefficient. Took a little bit more of a look at what they used, and they retested using the appropriate sieves, and the media came out okay at that point in time. There's also some contractor and temporary staff issues, particularly the first coating subcontractors' lack of care and experience, and also the general contractor had trouble finding qualified people, and they were ended up hiring people from the hall that didn't have any experience with installing filter media, and some of the work they did was hasty and ended up requiring some expensive repairs. There were a couple other issues that affected the replacement of the filter media. During this period of time, a lot of fires going on in the area, which resulted in some health concerns over the smoke, which shut down the operation for a period of time. And then they had some issues related to wind and sun, which damaged the tarping that they used. And then they also had rain delays due to the filters not being covered before the work. And then the city had a few issues related to their operations staff. The valves were not verified as being fully shut before lockout tagout. They were not familiar with non-standard operation of the filters. And then there were also just the project needs versus the needs to operate the plant. Some of the issues related to the existing facility, there have been some unrecorded field modifications of filters and equipment. As indicated earlier, the media was not installed according to the original specification. One of the butterfly valves sealing did not seal that allowed water into the filters. There's some equipment that was not functionally designed, such as the air scour blowers. The programming on the blowers was incorrect, and the city had been able to kind of survive with some fairly poor performance. And that there's some unknown issues, some known issues that weren't shared with everybody prior to construction of the project. There's some other construction-related issues. One of them involved placement of equipment. They had a gas-powered generator that was located, set up near the intake to the filter gallery, which they ended up setting off the fire alarm inside the filter gallery when it was operating. They also had brand new equipment that broke down, including one of the pressure washers was brand new that broke down on the first day of operation. So that basically their motto was that they needed to have a plan B, plan C, and a plan D, because Murphy's Law was in effect. So this is just some of the operational data for once they were able to get the filters replaced. The filter loading rate prior to the replacement of media was about 3.1 to 3.6 gallons per minute per square foot. And so far they've been able to increase to about 3.5 to 5, just over 5 gallons per minute per square foot. They've extended their backwash duration, or duration of filter runs between backwashes, and they've got a fairly good increase in the uniform filter run volume. And the capacity of the filters have been increased as well. So moving forward, the city plans to install Zeta meters to help them adjust chemical additions. They're going to modify their backwash monitoring equipment, and they're going to adjust their storage levels to meet the hydraulic gradient restrictions that they have. And they're going to start inspecting the underdrains on an annual basis, as well as annually sampling the media. The airflow monitoring equipment for their blowers was faulty, and so they're going to update and replace that. And then they're going to develop an updated process for adding or replacing media in the future. So the costs for the city on this, the contract award was $4.2 million, and they actually spent about $4.6 million. They originally anticipated it was going to take about 7 months to do the work. In reality, it took about 20. But they worked with the contractor to minimize delays to the plant due to unknowns. So the next steps are they're going to look at coding other portions of the 2006 improvements. Initially, this project was also going to include some coating repairs to the sedimentation basins and flocculation basins. But based on the bids that they got, they decided to put that off for the time being. They're also going to look at re-rating the plant to see if they can get 100 MGD out of these filters, or possibly even more. And then they're going to have to decide what to do about the 1964 treatment facility, whether they need to rehabilitate it or replace it. And I think some of that will depend on how well the new rating capacity of the 2006 plant comes out. And then they're looking at modifying water quality to address impacts on the concrete structures or use coatings for mitigation. That's all we have for right now. You have any time for questions?
Thanks, Milt. We're pretty much at the end of our time, but we'll try and go through a couple of questions that folks have had very quickly.
Yeah, I tried to zip through that as fast as I could.
Yeah, you did great. First question we had was on the garnet. In the existing filter bed, we saw that there was, looked like sand and anthracite, but there was a question about the garnet, but I think the garnet was just for the older filters, and this was...
That's correct. That was in the older filters, which we didn't touch as part of this project.
Okay, thank you. And then there was a question about the coatings. Do you know how the coatings have been performing today on the one that has been coated so far?
I have not heard anything in regards to how it's been performing so far, but I'd expect it, once they got the holidays fixed,
yeah,
probably good shape. Now, I did forget to mention that they did have one of their parge coats. The supplier provided a batch of parge that was contaminated, and as a result, on one of the filters, once the top coat was applied over the parge, it failed, and they had to go in and blast off the contaminated parge material, actually using some chipping hammers as well to get it out of there.
Yeah, interesting. And then the last question was the media sampler, the core sampler there that was in the photo looked pretty interesting. There was a question about if they made that or if they got it somewhere.
That was purchased.
Okay. And if you know where that was purchased, they'd probably be interested, but I don't know if you know that off the top of your head.
I don't know. I know
That's
that we
fine.
purchased it and gave it to the city after the job was finished.
No problem. All right. Thank you, Milt. We'll move on to Lida now. Lida, if you can see if I can hear you, get your audio up and going. Looks like you're still on mute, Lida. You can go ahead.
Okay, hi there. Let me get all set up then.
While you're getting set up, I'm gonna do your little bio intro. So Ms. Hakes has worked for the Portland Water Bureau since January 2019 and is currently serving as the Water Bureau's project manager for the 145 MGD Bull Run filtration facility design. Prior to joining the PWB, Ms. Hakes worked at the Alameda County Water District in Fremont, California for nearly 9 years, serving as a water quality and process control engineer, supporting a 28 MGD surface water treatment plant. And I can see your screen, Lida. It looks good to go and get started.
All right, I think y'all can see me now. It's a very different experience to be virtual, but at least I'm not in a freezing cold conference room, so that's nice. All right, so as Josh mentioned, my name is Lida Hakes. I work with the Portland Water Bureau, and this morning we'll talk about all the progress we've made so far for the Bull Run treatment program and a look ahead at what we have coming in the next 12 months and then to the program completion. So in terms of what we'll cover this morning, I'll give a quick background on the Portland Water Bureau for those of y'all who may not be familiar. Then we'll dive right into the Bull Run treatment program progress. I'm going to hit on our program management, project definition, piloting, what we're doing for the filtration facility itself, the pipelines to get to the facility, and also an update on WTC and our outreach. And we'll wrap it up with a look at the 12-month milestones and the long-term milestones. So the Portland water system serves about 1 million people, a quarter of the state's population. On average, it's about 100 million gallons of water per day. And it serves not just the city of Portland, but we also have 19 wholesale water districts. Our 2 water sources come from the Bull Run watershed. We have a filtration avoidance waiver right now, and then also the Columbia South Shore well field. The filtration facility, which will be a focus of this conversation, is right here next to our existing Lusted Hill facility. So in terms of the planned improvement projects, there are 2 main ones that I'd like to share with you. One we'll just glance at, and the other one will be the focus. So the top one is the filtration facility that we'll be building. It will remove sediments, microbes, and organic material. And we're under a compliance order by the Oregon Health Authority to have filtration online by September 27. Another project that we have also for a compliance order is our corrosion control treatment to reduce lead exposure from home plumbing. That will be online by 22. So the Bull Run treatment program is kind of a big thing to get our minds around, but we came up with a tagline for this of our water safe and abundant for generations to come. And that's really kind of guiding us as we work through this program. It splits off into the improved corrosion control treatment, which has Stantec as the designer, and the CMGC for that is MWH Constructors. And that's about all I'm going to say about that side of the program. We're really going to focus today on filtration. Filtration, we've broken down into the filtration facility. Our designer there is Stantec. They're also working with Crollo on that. Next, we have design for the filtration pipelines, and that's Jacobs. They're in contract negotiations right now, and the plan is to go to council to get approval on the design contract this fall. At the same time, we're working on getting our CMGC for the filtration facility under contract. That is going to go to MWH Hewitt, a joint venture, also going to council fall of this year. And then we don't have a CMGC yet for the pipelines, but we'll be advertising that early next year and hope to be under contract fall of 21. So again, we're going to focus here on this filtration side of the program. Oh, and I forgot to mention, I'm sorry, with the way my screen's showing. We also have our program manager is Brown and Caldwell, important part of our program. All right, so with so many different parties all working towards the same goal, it's really important for us that we focus on this concept of one team. And you can see here, we had a group come out in September of last year to tour the watershed and to go to our existing facility at Lusted Hill. And also note that it's pre-COVID. None of us are practicing social distancing. And it's a great opportunity to have our program management firm, ourselves as the Water Bureau, and Stantec all spend some time together and learn about our water system. That's me. But you already know that from the video. And I'd like to point out how our program director is smiling, Dave Peters, Michelle Cheek is smiling, Mark Graham is hiding, but I promise you he's smiling. Lots of happy, even our outreach person smiling. It was a really fun day. So everyone's happy so far on the project. So in terms of progress that we've made so far and kind of where we need to end up, I've dropped in a little copy of our schedule right here at a high level. You can see that we started out with facility planning. That's the filtration facility planning. We started then with pipeline planning. Facility design will start, and then pipeline design will both end our designs around the same time and go into construction, with pipelines finishing before the facility. Now, to get from our bilateral compliance agreement that was made in 2017 to our required completion from the Oregon Health Authority by 27, we only have 2,597 days, 12 hours, and 29 minutes. We have this countdown clock that we had in our program management office, so it's always a little scary every day when you come in and you see that number ticking down by the second. And so, having been in the program for a couple of years now, below here I have a couple highlights. In 2017, it was really about working with our agencies, working with OHA on the agreement, getting City Council to approve filtration, meeting with the EPA. 2018 is what we call our pre-planning portion of the program. So we focus on the procurement method, filtration plant location, which is our Carpenter Lane site. We're doing filtration, granular media filtration. At the time, we were thinking 160 MGD for our filtration plant capacity, and really starting to reach out to our community. 2019, the focus was project definition, a lot of workshops, studies, field work, touring other existing facilities to learn from them and see how their design played out. Getting our pilot plant up and running, program controls, program office, so lots of kind of setting the foundation that'll support the design and the construction. So when we think about our program management, this is what we're working on with Brown and Caldwell. Again, the focus is on one team. And so we wanted to try to eliminate kind of having multiple consultants kind of redoing things. So I broke it down into two portions that Brown and Caldwell is supporting us on. One is on coordination. So we have a singular entity working with our land use, our permitting, our traffic, our outreach, and many more. But I just want to highlight a few of the things that Brown and Caldwell is taking the lead on for us there. And also kind of, we wanted to have really great tools and processes in place. So we have our PMIS, it's our SharePoint site where all our files are stored. It's our program management information system. And really working with BC to develop guidelines and standards. The filtration facility is going to be enormous compared to the existing facilities at the Water Bureau. And so we really wanted to make sure that we had some great guidelines and standards that includes electrical, instrumentation and controls, process mechanical, building mechanical, solar design standards, and many more. So we really appreciate the work that Brown and Caldwell is doing to help pull those pieces together that then lays the foundation for our designers. So project definition, the big work there after all those workshops was to go to City Council and present some options to them. The one that Council approved is what we're calling the 2019 recommended option. From the raw water pipelines, it's 2 pipes with a large 2-pipe tunnel to bring water from our conduits to the facility. For the filtration facility, we decided to make it 145 MGD instead of 160 MGD with ozone and filters at a 6 gallons per minute per square foot filtration rate and a 16 mg million gallon size clear well with room to optimize those. On the finished water pipeline side, we're looking at 2 long pipes there. And when you put those three pieces together, the total cost is estimated to be 820 million. That breakdown is 590 million for filtration, 200 million for pipelines, and then we left 30 million as an other, and that really is to cover the cost of the known unknown. So property acquisition, permitting problems or issues to work through, challenges there. So we wanted to make sure we left money aside from that. Okay, so I'm going to dive quickly into pilot testing. Matt Gifford from the Portland Water Bureau gave a presentation at a PNWS Short School recently. So if you want much more information than what I'm sharing here, then feel free to reach out to me and I'll put you in contact with Mac. But what we're looking there is to really inform the design. So they did pre-oxidant testing of chlorine and ozone. We looked at whether to do pre-ozonation or intermediate ozonation. Direct and conventional filtration. We tested anthracite and granular activated carbon, JAC. We tested out, we started testing out 48 and 60 inches of media, and then we refined that to include a 54-inch media depth. We tested at 3 different filtration rates, 8, 10, and 12. We did a simulated distribution system testing to better understand the formation of disinfection byproducts. We did turbidity spiking, which you can see a little picture of here, how we made a nice chocolate milk for raw, and you don't want to drink that. And then you have a nice filtered water. It looks great. We have very low turbidity normally in our Bull Run water. And so we really wanted to try to stress test those filters at the pilot scale. And then also coagulant testing. All of that not just informs our our design, but it also is being documented in a final pilot study report, which we'll be providing to the state October of this year. In terms of future pilot testing, we'll again be looking at informing the design of the full-scale filtration facility. We're going to be looking at corrosion control, and you can see some jars there for different coupons. We'll be looking at solids dewatering and trying to better understand which polymers would work best for that. Coagulant testing, operational optimization, just really understanding how to use the equipment, what can we do, and staff training. We are an unfiltered supply right now, so we want to make sure our operators are ready day one when the filters go online. Looking at our filtration facility itself now, so I've broken it up into design and the construction, the CMGC. So Stantec is under contract, and in terms of our preliminary design, the phase run right now, we have had a lot of workshops. We've completed 26 so far. We have 3 more planned before our basis of design report comes out. We had 5 Get Smarts. We felt it was really important that we gave kind of a preview of the topic to staff so that they can better learn the material if it's something they've never been exposed to. So we did that for filtration. We did that for the disciplines, electrical, INC, SCADA. We just wanted to give everyone an opportunity to get smart and better understand the material before we ask them to start making decisions on it. We also completed knowledge transfers, which were discipline specific. This is where it was an opportunity for us to sit in the room with our designer, Stantec, and with our program manager, Brian Caldwell, and let them talk with each other and to each other about what progress they've made so that then Stantec could carry it on and not duplicate any efforts. And also working closely with the program manager on coordination, permitting, land use, site access is a big deal for us. How are we going to get into the site? How are we going to get out of the site? How are we going to do construction traffic? And also we needed to coordinate our pipeline depth with the pipeline designer. So at what elevation is the pipe coming in for the designer to take over responsibility for? And at what depth is it coming out of the clear well where the pipeline designer will then take responsibility? We need to make sure those pieces match up. And then completing a geotechnical investigation. All that's working towards a draft BDR, which will be submitted in November 2020 and final in January. On the CMGC side, the construction side, so the RFP was advertised in December 2019, and MWH Kiewit joint venture is in contract negotiations with the Water Bureau right now, and that'll go to council this fall. So looking at the preliminary design for the filtration facility, we had a lot of workshops. So I just want to give kind of a little snippet here of all the different topics we've had and how they sequenced into each other. And at every point, we made sure that we came out of it with the decisions we needed to provide to the designers for the basis of design report. And we just had our corrosion control and procurement on Tuesday of this week, and in a couple of weeks we'll have our operations and maintenance plan. Now this is where I'm going to do a little public service announcement because pretty much every single one of these workshops was done remotely, which was not at all what we were expecting. It's really great when you can be in the room with everyone and you can see that nonverbal language, who's nodding, who's frowning, who looks completely lost. So I wanted to share some tips real quick. One is I recommend a duration of 3 hours or less. People really can't handle much longer than that, especially virtually, you'll lose them. We recommend a 15-minute early login period. It allows everyone to come in, log in, make sure all their equipment is working. We can hear them, they can hear us, they can see the screen. We have found that if you're on our VPN for the Water Bureau, you're not going to get good audio. If you're plugged into some of the laptop docking stations, you don't get any audio. So that little 15-minute period was a great time to get people on and early. They could step away and get their coffee, but we always started right on time. Also, we found it was really helpful to have well-defined roles. So the presenters, their job was literally just to present. They were narrowly focused. They just got through their material. The host was the one who could see, we used WebEx as our platform. That's the one who could see who was making the random background noise and wasn't on mute, and he could quickly mute them. They could see who had their hand raised so he could call on them. We also had moderators. In this case, Jude Grounds and I, Jude is with Crowlow and is on the design team. Our job was there to kind of keep the conversation moving, keep an eye on the time. We were working behind the scenes with Mark Graham, our project manager from Stantec, to decide this is a rabbit hole. We got to change the conversation, or we're not hearing from the right stakeholders. We need to pull them out of their shell and get them talking. If it was kind of feeling dry and boring, we had to kind of lighten the mood a little bit to keep everyone awake. And then also we had someone who was our pollster. They were the responsible one for taking over the screen share, presenting the poll, closing it out, which leads me to incorporate polling. It's really hard when you're trying to get 30 people in a room virtually and drive to a decision. So we incorporated polling as a way to document what everyone's preference was. Also, be sure to have clear rules of engagement. What are you expecting? How do you want people to communicate to you during the workshop? And also try to make it fun. We were kind of goofy, I think. And it made it a little lighthearted when you're getting through really deep material. My personal workshop rules are have your hand raised. When we have 30 people on and people are trying to talk over each other, it's super distracting. So we had the hand raised function in WebEx, and Jude as the host was able to see who had their hand raised, and we're able to call on people. And they could raise their hand at any point and we'll work them into the conversation. We didn't make them wait till the end. Also, we shut down the chat function. That drove me crazy because you'd have the presenter speaking and then you'd have these side conversations and people were splitting their attention. It was really hard to keep up with the material and the chat function. So we shut that down. We did encourage everyone to be ready to participate. I called it dealer's choice, which probably made everyone quake in their boots because I would just call on people randomly. It's mainly the subject matter experts I really wanted to hear from, but we wanted to make sure that we were getting people who maybe were a little shy or quiet to speak up because they have really great feedback that we needed to hear. And then finally, because we are in this virtual environment where you can't see people, we do want you to participate, but we don't want you to repeat what everyone else just said because otherwise that burns through your workshop time. So those are my little workshop rules, and that's the end of my public service announcement. All right, so the good stuff. Where we are from our preliminary design is I'm presenting our integrated process flow diagram. This is a great point to do a little snippet or look at the presentation later because there's a lot of information here that I'm not necessarily going to go through in detail. But we come in from our splitter box. We're going to have pre-ozone. Our ozone is going to consist of side stream ozone injection. And in terms of what we're trying to handle with our ozone, we're really looking for algal toxin destruction. We're estimating that at about 1.5 milligram per liter applied dose at an 8-minute hydraulic residence time. We're using liquid oxygen, and we will be having a standby ozone generator. Moving to the rapid mix, we're going to be having pump diffusion. When we look at our flocculation, we're having vertical turbine flocculators and going into the sedimentation basins, we're going to have telescoping sludge collectors there. Our filters, we're designing them for anthracite and sand media and a maximum depth of 72 inches of media. The clear well, we're going to have a pumped backwash to support the filters. We're going to have 2 basins that are 2.4 million gallons for our CT, and then 2 storage basins that are 3 million gallons each. Our solid side, I don't have it shown on the figure, but in terms of our solids, we're going to have plate settlers for clarification. The filter to waste will go back to a shared recycle tank and then to the inlet. And we're sizing our solids handling to handle normal solids produced at our max rate of 145 NGD and 1.5 NTU. But we're also making accommodations to run at extended periods of time for 145 million gallons per day at a higher NTU of 24 NTU. We're gonna have gravity thickeners and also centrifuges. All right, so that's how we're gonna make the water. Now I wanna present 3 of the site layout options we're considering. The first one is a circular campus where you would enter from the north, and then you can go through the process or you can go around it. We have our admin building and our maintenance building, and then the process units over there. Next is our option 2, a linked campus. Again, prioritizing the northern access route with the southern exit, and different ways to access the basins. And then the third is prioritizing a southern entrance. So at this point, what our site utilization team is reminding everyone at the Water Bureau is they're not asking us to pick one option at this point to advance. What they're really looking for is us to dig into the details of what is it we like and what is it we don't like about the options, so that they can then put it together and present 2 final options for consideration at the end of September. So just like a little preview of whatever 3 options we have before us. All right, in terms of geotechnical activities, we've completed our initial on-site investigation. We have an updated geological interpretation and subsurface conditions identified. We've identified the site geologic concerns. We've performed our preliminary ground deformation analyses, and they are presenting the geotechnical recommendations to the Water Bureau and our Geotechnical Technical Advisory Committee, the GTAC, right now. Here is a figure of our site. And this right here in the middle in the blue is the optimal build area. We have 2 steep areas, one that's a low risk for slope movement and one that's a very high risk for slope movement. So we need to have a great setback from there. Okay. Looking at the pipelines now. So I've broken it up into project definition, design, and CMGC, construction. So we are working towards getting our alignments selected. That'll be in October of this year. In terms of field work, they've been very busy with neighbor outreach, surveying, geotechnical evaluations, environmental studies, and cultural resource assessments. And just accessing easements is a challenge, getting property owners to allow us on site on their property. That project definition report for the pipelines and the facility too is coming out fall of this year, October. In terms of design, they have a designer, Jacobs Engineering. They are in contract negotiations right now and hoping to go to council this fall and get their notice to proceed. The CMGC, they plan on advertising early next year, Q1. You can see they're all nicely spread out right there for their investigation. You can tell the pre-COVID and during COVID pictures pretty easily. All right, so what are these pipelines going to look like? So on the left-hand side, we have our raw water pipeline alternatives. On the right-hand side, we have our finished water. It's kind of funny because when you look at the site's in the middle and raw is on the right, finish is on the left. So that just threw me for a loop. But we have all these pretty little spaghetti colors of different options that we're evaluating. So we're looking at cost, we're looking at constructability, we're looking at permitting. There's lots of considerations for us in terms of picking the best alignment. So that will be coming October. So in terms of, so that kind of closes out what we've done with the facility and what we've done with the pipelines. Now the question is, how do we pay for all this? So I wanted to update you all on WTC. For those who may not be as familiar, it's a unique federal financing opportunity for U.S. water and wastewater infrastructure projects. Benefits the ratepayers, creates local jobs, but there are procurement requirements associated with that. To give you a sense of our timing, and I know when did we start this effort, so we submitted a letter of interest in July of 2019. October of 2019, we were informed by the US EPA that we have an invitation to apply. We've been working with the EPA and our finance group at the Water Bureau to get all our ducks in a row, and our loan application was submitted April of this year, and we're expecting to close in October. When we look at the loans that we're asking for from the EPA, it's $727 million in water loans, and it'll help reduce our future rate impacts by saving us an estimated $324 million in debt service. Finally, not just you need money, but you also need to have outreach with your community. It's kind of like flossing. It's going to be really painful if you don't do it. It's kind of annoying when you have to do it. Outreach is very, very critical for a successful program and a successful project. So we have a site advisory group that we're meeting with on a monthly basis. We also are working on drafting a good neighbor agreement. We're holding online meetings because of COVID right now. We have done neighborhood door knocking and door hangers, and we have a lot of events. We've done, last year we had a BBQ&A where they were able to ask us lots of questions, and we're having a virtual open house this September. We also have mailings and email updates. If anyone is interested, I've put the program webpage up here. And Benita Oswald is our Bull Run communications lead. She's amazing. Her an email address she monitors is right here along with her phone number. And as you can imagine, we're out in a rural part of Oregon, and the neighbors aren't so happy, but we're really trying to work with them collaboratively to make the best facility we can make. And you can see here, they are out in full force in their beautiful blue shirts, and the Bull Run Water Guardians are wanting to stop our project. So we just keep trying to work with them and make it a successful delivery for both. In terms of what's happening over the next 12 months, I've broken it up into program, filtration, and pipelines. So from the program perspective, the pilot report will be submitted to OHA in October. We'll complete the project definition report this fall as well. Close on that WIFIA loan. October is going to be a very busy month now that I look at all these dates. Finalize our good neighbor agreement, and we just started this month, initiating specialized pilot testing. From the filtration perspective, we're going to complete our BDR, so the draft will be submitted to the Water Bureau in November with the final in January. We're anticipating that the notice to proceed to MWHQ at joint venture will come this fall, and we will initiate and complete 30% design. Pipelines, notice to proceed will go to Jacobs this fall as well. We'll put out our advertisement for our CMGC and again, initiate and complete 30% design. So it's a lot of work we've done. It's a lot of work we have coming up for this next 12 months, but we have a lot to complete before the September deadline. So we'll be going through our detailed design, getting those submitted for approval to the state, and then starting in on our construction. In the meantime, we're going to be working with our partner agencies for land use and permitting to make sure all those ducks are in a row, and transportation. And it's going to be a really busy next 2,500 and something days. So with that, I don't even know what time it is, but maybe we have time for questions.
Thanks, Lyda. Great presentation. If there's any questions, go ahead and type them into the Q&A box. I haven't seen any so far.
Is that because I said no chatting?
They're all too afraid. They're like, don't type in anything. So thanks for sharing everything about the exciting to see such a complex project come together.
Sure.
But I guess with that, there's not any questions aside from some folks saying that you did a great job. So
oh, thank you.
Thanks for that. And thanks again to all the participants for joining us in our third and final Water Treatment Committee webinar. We do not have any more webinars currently in the works, but I know the Pacific Northwest section is putting together 4 6-hour virtual webinars in place of the Boise conference that was going to happen next year. And that'll be coming out in the next couple months. So stay tuned for that. And if you're interested in participating in those, definitely log on to the Pacific Northwest section of the AWWA conference website to find out more details. All right, thanks again, everyone. We will follow up with all your certificates and other fun follow-ons to make sure everyone gets credit for PDHs and CEUs here in the coming weeks. So stay tuned. Thanks again. Take care, everyone.
Thanks. Bye.